Yeah.
Okay, good day, good day, everyone. My name is Diana Gomez. I will start the last day of talk of the annual International Conference of Brain-Inspired Cognitive Architecture for Artificial Intelligence. I will be the chairman during this presentation block. We shall start with Anastasia Piven's presentation. Anastasia, are you ready to share your screen?
Hello, I'm going to be sharing the screen, Ksenia. I'm with Anastasia. We've talked about, we sent an email that I'm going to be the presenter. But I'm ready to share the screen. Can I?
¿No está Anastasia? ¿No se escucha? A mí se me quiere la chica. No sé qué soy el. Ya estás todo.
Okay. Anastasia, can you share your screen, please?
Yes.
You have 15 minutes to present your work, followed by 5 minutes of the question from the audience. Anastasia, you can start, please.
Yes. Hello, everyone. My name is Ksenia. I'm going to be presenting the research that we made with Anastasia Piven and Professor Jan Troel on the base of Free University in Amsterdam. And the topic of our research is an adaptive network model for aggregation and pattern-like propagation of alpha-synuclein in Parkinson's disease. So Parkinson's disease is considered to be synucleinopathy. It's one of the main neurodegenerative diseases, which is defined by the loss of dopaminergic producing neurons in the region of brain called substantia nigra. So the Parkinson's disease is unspecifically characterized by symptoms such as bradykinesia, rigidity, and resting tremor. And the protein called alpha-synuclein is thought to play the key role in the development of this disease. So we have protein monomers of alpha-synuclein, which are normally present in brains, but in some cases they gain an abnormal formation and leading themselves as prions, which means that one specific monomer or oligomer might cause the other proteins, normal proteins present in brain, to gain an abnormal conformation, what leads to formation of Lewy bodies and therefore the loss of neurons and brain damage. But along with alpha-synuclein, growing evidence exists that lipids with alpha-synuclein play a role in the development of neurodegeneration. And what's going on is lipids and alpha-synuclein, they aggregate together, wasn't just simple aggregates or clusters of alpha-synuclein and lipid vesicles. It leads to alpha-synuclein/lipid dyshomeostasis. And a few mutations in specific genes were found to possibly play a role in the development of this abnormal formation of lipids and alpha-synuclein. And so after the aggregation of alpha-synuclein with lipids exists, the 4 postulated ways of further propagation of alpha-synuclein in brain might take place. So the first one might be through synapses or synapse-like structures, through nanotubes, which is basically bonds, so connection between one cell and another, incorporation by simple endocytosis and exocytosis, so vesicle inside or attached to alpha-synuclein, leaves one cell and goes into the another, and also through receptor-mediated uptake. And so based on the background information, we've created the conceptual model for our network. So we start off with the mutation in enzymes that are responsible for lipids present, mutation in alpha-synuclein responsible genes present. So the first box here, which is for enzymes, leads to enzyme dysregulation and leads to lipid dyshomeostasis. And the same holds for alpha-synuclein, leads to alpha-synuclein homeostasis. And at this stage, different risk factors might intervene or make it worse. And so this homeostasis of alpha-synuclein and lipids leads to alpha-synuclein gaining toxicity, what leads to further seed formation, meaning this seeds of alpha-synuclein with lipids might leave the cell and through the propagation ways I've talked about, and the aggregation itself would also lead to seed formation. And so at this point, different protective factors might possibly intervene, which we don't know exactly how they do this and what exact protective factors might exist. A bunch of studies have shown that some interesting protective factors might exist. For example, smoking or coffee consumption or ibuprofen consumption might play a role as a protective factor in neurodegeneration development. And some risk factors such as infections or dairy consumption, as well as metabolomic syndrome, and as well as different medical conditions. So after the seeds were formed, 4 our postulated ways of propagation take place: synapses, receptor-mediated uptake, propagation through nanotubes, and exocytosis, endocytosis. And together, they are collecting to the alpha-synuclein general level of spreading in the brain, which leads to neurodegeneration. So now you can see the 3D model of for our simulation, and on the base level you can see the conceptual model, and you can see also 2 higher levels. Second adaptive level has 4 B states. Let's see what they mean. For example, lipid homeostasis leads to alpha-synuclein toxicity, but both the more lipid homeostasis dysfunction we have, the more alpha-synuclein toxicity we have, and they both gonna result in more alpha-synuclein toxicity. The same holds for alpha homeostasis dysfunction and alpha-synuclein gaining toxicity. The more alpha-synuclein dysregulation we have, the more alpha-synuclein toxicity we have, but they both going to result in more alpha-synuclein toxicity itself, and it holds for every V state we have. For example, aggregation and seed formation, more seed formation as a result, and of course, the general level of alpha-synuclein spreading in brain and neurodegeneration. And on the 3rd level, you can see 4 V states which stand for speed factors for each of the V states we have respectively. So now going to the cases, to the simulation itself. So we've created two simulations for two different cases. And so the first scenario is when we have mutation in genes of alpha-synuclein and enzymes responsible for lipids. And so these mutations are present. And we have as well protection factors, but they are not sufficient to do anything with the start. So with the start of neurodegeneration. So you can see the simulation here. One by one, these lines going up represent the start of neurodegenerative process. 4 horizontal lines over here stand for different ways of propagation of alpha-synuclein, because the recent studies have shown that the different methods of spreading of alpha-synuclein in the brain, they have different levels and they are responsible for different fractions of general level of alpha-synuclein. For example, the one that is thought to be the least important is simple exocytosis endocytosis line over here, and the most important one is thought to be receptor mediated, which you can see up top over there. And so the level of aggregation stays the same after it has been put to the maximum it can be in specific cells. And the repetitive lines over here, these are graphs created with step mode to represent risk factors and protection factors. Let's look closer to this simulation here. What we can see is when risk factors drop, the level of lipid homeostasis disorder and alpha-synuclein homeostasis disorder also drops just a bit. What means that when risk factors are not present at the same high level and neurodegeneration is already present in brain, lipid homeostasis and alpha-synuclein homeostasis might be slightly better than it was before with risk factors, but it's not sufficient for neurodegeneration with which is an orange line over here, to change just a bit in any side. And protection factors, which is a blue line over here, they might overlap with risk factors. And you can see that when protective factors drop, means they are not present. The level of alpha-synuclein homeostasis and lipid homeostasis disorder slightly goes up. And you can see that by the absolute values of this growth or drop, you can see that the drop when risk factors are not present, it's more in absolute value than the growth in protection factors drop, meaning that risk factors play a more significant role and they intervene in higher levels than protection factors when we have neurodegeneration present in brain. And of course, when these both things are present, we cannot reverse neurodegeneration. That's why it continuously stays at the same level. Now moving on to the second case, the scenario is that mutation for alpha-synuclein genes and enzyme genes are still present, but protection factors are predicting an older age of onset. And you can see the simulation here. So the lines for the spreading, they are the same, but neurodegeneration, the last orange line we had, is growing slower. It means that neurodegeneration is still existing in brain, but it predicts an older age of onset. But it's hard to tell how much older, because the patients with gaining Parkinson's disease, they are already old. So the difference between either it was because of protection factors or because of risk factors going up or down is hard to tell between this one or either the previous case, but we had less protection factors, or it was just a case with a person that it was already too bad for them or too good. So it's hard to tell either this neurodegeneration going slowly of how much of older onset we can talk about. And so in conclusion, we have a model now that unifies the processes of aggregation and further possible propagation pathways of alpha-synuclein. And the main focus was on alpha-synuclein and lipids, which is a hot topic right now in neurodegeneration and Parkinson's disease, and how homeostasis of alpha-synuclein and lipids can be alterated by different risk or protective factors. And The received patterns present different ways of how risk and protective factors can play roles in neurodegeneration, although we still don't know the exact patterns, and that could be a topic for future research. Thank you very much for attention.
Anastasia, thank you so much. Now we will proceed with a question from the audience. If any has any question, please raise your hand. There doesn't seem to be any hand raised. So thank you so much, Anastasia, for your presentation.
Thank you.
Okay, thank you. We will proceed with the next presentation. Evgeny Vitiev, are you ready to share your screen?
Yeah, I am ready to share my screen, and I will run my video. Yes, I will share.
Okay, you have 50 minutes to present your work, followed by 5 minutes of questions from the audience.
Yeah, yeah.
Okay.
I can start?
Yes.
My report is devoted to the task-driven approach to the artificial general intelligence. It combines the following important approaches. First, it is explainable and works in terms of subject domain ontology. Second, it efficiently solves a wide range of tasks that are formulated in terms of executable specifications, which automatically generate algorithms of these task solutions. And third, it models a cognitive process, which are considered as a special type of tasks. And in particular, it models a physiological theory of functional systems of brain activity. Let us consider artificial general intelligence. IGI is not anthropomorphic. The planet has shown that human nature is not necessarily prerequisite for solving cognitive tasks of a variety of degree of complexity. According to AGI, it is to some degree can be potentially possessed by both a person or a living organism with a highly developed central nervous system or an abstract robotic system. Famous developers of AGI gave the following definitions of AGI. Ben Gertz, general intelligence is the ability to achieve challenging goals in challenging environments. Shane Lang and Marcus Hatter. Intelligence is measured by the agent's ability to perform successfully in a wide range of environments. P1. Intelligence is the ability of a system to adapt to its environment, working with insufficient knowledge and resources. As a result, in the famous book on AGI, Strong Artificial Intelligence, published by Sberbank, the following definition of AGI was given. It is the ability to solve cognitive tasks in general, acting purposefully, adapting to environment through learning, minimizing risk, and optimizing losses to achieve their goals. In this report, I can propose that task-driven approach satisfies the definition of AGI and also provides an anthropomorphic solution of a wide variety of tasks. Let us consider the informal definition of the task-driven approach. The task is defined if its formulation contains an indication of the subject domain to which the task belongs, domain ontology, knowledge about the subject domain, initial data, and hypothesis. To what request question formulated in the task we should receive an answer. The criteria for satisfying the request to determine in which case we can consider the answer to the request question was obtained. In what context should the answer to the request question be sought? What is the goal we pursue in solving the problem? That is, what we expect from the result, and what is consequences. Task-driven approach supports that the purpose of artificial intelligence is to automate the solution of tasks. Therefore, task requests must be formulated in terms of executable specifications. If we take the sigma definability of computations as a basic model of computations, in accordance with the book of Virchow, Definability and Computability, Novosibirsk, 2000 year, and checking the truth of signal formulas on a constructed model and its list of superstructure, then this gives an algorithm for solving the task as a general recursive function. If we use delta zero formulas for the task specifications, then the task solution can be obtained by primitive recursive functions. If the primitives of the language are polynomially computable, then and a specification of the task use sigma zero formulas, then the solution of the task can be obtained by in polynomial time. The formal definition of the task in terms of semantic modeling is defined as follows. It is assumed that we have a multi-sorted constructed model together with this superstructure on M, which is kind of a basic compute. The task, the main model under consideration is formulated in the signature of the predicate calculus language of this basic constructed model, together with its list of superstructure as a set of sigma definitions. It has sigma formulas and sigma terms of this language. A query to the domain model is often defined as a sigma formula. By the solution of the task, it means a set of constants that makes the sigma query formula true. The truth of sigma query formula is the criterion for the task solution. Let us consider the task concept in cognitive science. A generalization of the task concept in cognitive science is the concept of a goal. The goal cannot be achieved without criterion of its achievement. Otherwise, it can always be considered that it has already been achieved. Therefore, the formulation of the goal should always be accomplished by the definition of the criteria for the goal achievement. Achievement of the goal gives a second result. The goal and the criteria for the goal achievement must match each other as K to a log, as shown on the picture. Here, blue indicates a goal, for example, trust, and red indicates a substance that needs to be found to quench trust. Whether the substance quenches trust or not is determined by the criteria for the goal achievement, indicated by red. If the criterion is triggered, then the goal is achieved, and the trust and the right substance is found. Then we get the result, the quenching trust. The only physiological theory in which achievement of the goal and getting the result is considered as a task solution by the brain is the theory of functional systems by Piotr Kuzmichenko. This theory also reveals the physiological mechanisms of the goal achievement, task solution by the brain. Perhaps the most dramatic moments in the history of the brain study is the fixation of attention on the action itself, and not on its results. We can assume that the result of the grasping reflex will not be the reflex itself, but the totality of apparent stimuli which corresponds to signs of the grasp object. It was written by Dr. Convolutional. The totality of apparent stimuli is the criterion for achieving the goal in the functional system theory. Therefore, a necessary condition for the purposefulness behavior of an intelligent agent is goal setting, which includes the criteria for the goal achievement. According to Piotr Kuzmichin Anokin, the certain mechanism functional systems that provide purposefulness behavior have the same architecture. The formal model of this architecture is presented in the paper follow. Architecture. Afferent synthesis. The initial stage of behavioral act of any degree of complexity is an afferent synthesis, which includes the synthesis of motivational, excitement, memory, situation, or trigger interpretation. Motivation, excitement. Goal setting is carried out by an emerging need, which is transformed into motivational excitement. Motivational excitement retrieves from the memory also the entire sequence and hierarchy of results that must be obtained for the goal achievement. Situation and trigger interpretation. When interacting with the experience length from the memory, situational interpretation determines what and how it can be done in a given environment to achieve the goal. Trigger interpretation is also situation, but it only relates to the time and place of the goal achievement. Decision-making stage. The stage of apparent synthesis, motivational excitement, can extract from the memory several ways for the goal achievement. At the decision-making stage, only one of these ways is chosen, a specific action plan. Acceptance of action results. Motivational excitement also retrieves from the memory the entire sequence and hierarchy of results that must be obtained to carry out the action plan. The sequence and hierarchy of results is called the acceptor of action results. Reinforcement and authorization stage. If the behavioral act leads to the goal achievement, then the entire sequence of actions is reinforced and recorded in the memory. Since the real situation is always somewhat different from the situations that were retrieved from the memory, then inevitably there may be mismatches between the expected results and actually coming in the representation about the real action results. In this case, the restructuring of apparent synthesis occurs and a new decision is made to achieve the goal. From the point of view of the brain approach, the task solution by the brain is formulated as follows. The main model is the external goal in which purposeful behavior is carried out. The request to the main model is a need that must be satisfied. Let us denote it by the predicate P0. By solution of the problem, we mean an object A or situation, an unit of external world perceived by the set of afferent stimuli of object A, which makes the predicate P0 true, which leads to satisfaction of the need. The truth of a predicate is the criterion of the task solution. There can be several specific plans to achieve the goal that makes the predicate true. And the decision-making stage is choosing one of these plans. Let us consider the scheme of functional systems in terms of probabilistic causal relations. To do this, we first will define a probabilistic causal relation. It is satisfied the following two conditions. First, Cartwright condition on probabilistic causal relations. If we have a relation R is equal to H1 and etc. HK follow H0, then its conditional probability is strictly greater than the conditional probability of its subrules containing strictly less conditions. Second requirement, a requirement of maximal specificity. I will not define it formally, but informally, it means that a probabilistic causal relation should use maximum available information that can increase the conditional probability of the rule. We can prove that in this case, predictions of such causal relations are carried out without contradictions. This was proved in the following paper. The scheme of functional system works in accordance with its architecture described above. I will provide the most illustrative computing experiments which demonstrate the work of our model of functional system. Let us consider an electronic model of mnemonic developed at the Institute of Computer Science Systems by Polyana, which takes into account the sequential work of muscles and their interrelation, friction on the surface, and other elements of the structure of the mnemonic. We took this model and put into it our model of functional system. It turns out that the mnemonic can learn its natural movements within 100 or 100 feet around samples. And after that, it finds its natural movement. In the next experiment, we model a group of mouse, each of which has its own functional system, and at the same time they can exchange its experience in the form of rules given on the right. As a result, they can learn to achieve rather quick. There are main books and articles which were devoted to this theme. Thank you for your attention.
Vitir, thank you so much. Now we will proceed with the question from the audience. If anyone has any question, please raise your hand.
Hello. My question is the following. There are multiple things that can be goals. For example, I can have a goal to reach a specific situation, which is somewhat simple to solve, or I can have a goal to become rich, which is not so simple to solve. How do you plan to deal with these more difficult kinds of goals, just like becoming rich? Is there a way to specify that, or how the system can cope with these kinds of goals?
Yes, the system can be made and extend with utility function. And if we will use utility function, we can include several goals. So it is possible.
Oh, okay, thank you.
Another question? Okay, Vichir, thank you so much for your talk. Now we will proceed with the next talk. Salihana, go if you're ready. Nago appears to not to be present. Is there any other author for this paper present?
Okay, we wait.
We will wait some minutes.
Okay, good morning. I'm Felix Ramos. It's for me a pleasure to present our next keynote speaker. His name is Armin Sikodochian. He worked in IBM, and today he is going to talk about Watson Studio and Auto AI. He is going to deal with problem, or rather he is going to present how those tools can help us to deal with accuracy and mainly the problem that we have as humans to interact with cognitive machines. So please, Armin, go ahead. You have time, and that will be great for us to listen to you. Go ahead.
Thank you so much, Felix. Ladies and gentlemen, welcome. Let me start by sharing my screen. Desktop. There we go. Slideshow, right from start. By the way, a thumbs up. Everyone can see my screen just fine?
Yes.
Felix, excellent, excellent. Thank you. Move this one out here. Nice. Ladies and gentlemen, I must admit, this is not a research paper. Although artificial intelligence is the topic, not so much brain inspired. And that's okay. Hopefully you would find this a breath of fresh air. It's my primary audience in here are mostly in their 20s. They are graduate students or undergraduate students who are excited about the field of data science and AI engineer, who are thinking, what is it like to work at one of these giants, IBM, Facebook, Twitter, Meta. So I'm going to bring that sort of a approach, that sort of a mindset to the crossroads of these two disciplines, really. And also perhaps give you a little inkling of what it is that we are doing at IBM, what are our mindsets in here. All right. Let me minimize this. So this is what we're going to talk about today. The case of the missing bullet holes. A data science story before it was called data science. You know, when we were hiring, I interviewed data scientists at IBM. The first question isn't, do you know Python? No. What we're looking for are traits. Are you eternally curious? That's what I want on my team. Constantly is asking why. And can you tell stories? I want a storyteller. In this forthcoming hour, I'm going to be telling you a whole bunch of stories. You know, we have our data sets, we visualize them, and now we have to tell a tale of what it is that we discovered. And the case of the missing bullet holes begins us just fine. About cognitive systems, understand, reason, learn, and interact. Let's talk about those in more depth. From inferential statistics to calculus 2. I really find it fascinating how, given your data, starting from structured data and using things like logistical regression, SVM, random forest trees, at some point your parameters get to the point that just brute statistics is not enough. And we have to bring forth deep learning networks. All of a sudden, you know, my dean, I'm also a professor at 2 universities. I'm in Boston. So one of them is 10 minutes away. The other one is online. My dean said, hey, this is the computer science department. So you want students from engineering and computer science and so forth, right? I said, no. The students that I would like, I want them to be from varied disciplines. You know, I want them from the nursing school, from the psychology department, architecture school. But the one thing that I really like to see in my students is a strong sense of statistics, first and foremost. That, to me, is the prerequisites to this discipline. Demo Auto AI. Now, I think perhaps the value in this talk might be in showing you how this beast works. We're going to build and deploy a model. All of this in as little time as possible. And I love this final topic. I really hope we get a chance to talk about this after the demo. With live demos, you never know. You click and you have to wait. We'll see. But what does IBM think about artificial general intelligence? How far are we? Are we getting there? What work are we doing towards that? Really fascinating. Here we go. Abraham Wald and the missing bullet holes. Mesdames et messieurs, ladies and gentlemen, señores y señoras, no, another one, Mabibi na Mawaba. Let me take you back to World War II. It's funny now that I say this slide after the war that has happened, it has a different connotation to it. But back then, Allied airplanes, they would come and land in England, riddled with bullets, the fuselage, the wings, the tip, brutalized. So the powers to be said, look, we have to reinforce these airplanes. Remember, this is World War II airplanes. Some of them are propeller and a few of them are convertible. You can open the roof up in the air. So we can't just put heavy metal all over the place. They knew of an Abraham Wald, a statistician. Oh gosh, tender age of 48. He founded the field of statistics and he spent some years at Columbia University. They said, Abraham, come, help us. How do we do this? There he is. There's Abraham Wald. He said, okay. So he did what back then it wasn't even called data science, what a data scientist would do, gather data. So he went and started counting the bullet holes. See, he's counting them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, endless. And then after 2 days of counting these bullet holes, he goes back to the powers to be, the generals and so forth, and says, I know where you can reinforce the airplane. Oh, really? Where? In all the places that do not have bullet holes. That do not have bullet holes. After all, they made it back. It's the ones with bullet holes elsewhere that didn't even get a chance to come and land in here. See, this sort of a prediction, this sort of a judgment is something that is elusive from the best AI systems today. Because what Abraham Wald had is experience, world knowledge, not just training. Very, very interesting. Let's see now how can we get close to the predictions that Abraham Wald made. See the data that we're talking about? This is the structured data, CSV file, Excel spreadsheet, and SQL calls you make from Oracle, Microsoft SQL Server, IBM DB2, fantastic. The data scientists that work in the structured data area, they sit in the office. Imagine I'm sitting in the office, and the boss comes and says, hey, Armin, I want you to find out how come we're having employee attrition. Okay, I take the CSV file, I do some analysis with it, and maybe bring up Jupyter notebooks, do some, import some libraries, see some visualization. Fantastic. But the data scientist that's working in this area, I call it the modern data scientist, it's working in this area, has to wear a jacket, has to put on the coat, has to go outside, feel the weather, take measurements from the sensors, collect the images from the street cameras, bring them back. The data scientist that's working in this area is working with what it is that you don't know that you don't know. I love this concept. There are things that we know how to be a sibling, a parent, drive a car, the science and technology we're studying, how to cook food. We know what we know. And there are things that we know that we don't know. I'm a little bit murky about what happens the black holes there with the event horizon and so forth. So I can use a chat box. I can ask, at least I have a question to ask. Then there are things that I don't even know I don't know. I don't even have a question to ask. That's insight. That's what I want to my data scientists to garner, to get from this section. Can you give me an example of what it is that you don't know that you know? That you don't know that you know. I can't see the chat. I mean, I can open it, but too many windows in here. You know, well, fate. Fate. For example, I might go up and I see this big door. I would open the door. Just no end. No end up there, no end. It's a big jump, big fall. I can't even see the bottom. And I'm going to say to my friend, I'm jumping. He's like, Armin, what do you mean you're jumping? He's like, no, if I jump, only two things will happen. Either I will learn how to fly or I will land on something soft. Well, really, do you have some data points, analysis? No, because I have faith. Interestingly enough, you could say that's a definition of faith. Really, really, really philosophical conversations one can have. This is very interesting, a brief history of AI and ML. Notice 1956, Dartmouth College, New Hampshire, 3.5-hour drive from where I am. This is where artificial intelligence was coined. Marvin Minsky, John McCarthy, Alan Newell, you know, there were 8 of them. They gathered and over a period of 10 days. They said, wait a minute, if this is how neurons work, they're firing on and off. There's always a potassium ion channel going on in my axon, and these are the dendrites, synaptic junctions back at the end. And it's on and off. It fires and then it stops. How can we do this with code? Logistical regression came into play, for example. Some interesting things to note in here is the two winters, the AI winter of this period. This mostly happened because computing power wasn't there to work with the math that was at play. There was another AI winter around the 82, 83. This is mostly because of government funding. It became like lost when it went away. And then work started again. Over here, we had the Jeopardy game, Gary Kasparov. DARPA's Grand Challenge. This was really cool. 2011, Watson wins Jeopardy. I was involved with that, ladies and gentlemen. I've been at IBM for 20 years now. It's funny enough when I talk to people and like, hey, John, how long you been here? 10 years. Ah, you're a baby. It's typical of most of us, that most people that I know that have been there close to a decade, plus or minus. It's a beautiful thing. So halfway through my tenure, that would have been 2011, all of a sudden this Watson thing started at IBM. It was hard to get into that. You had to apply. It was like Senate grilling, that the panel would sit there and they would ask you a question, big interviews and so forth, and either you got it or you didn't. I landed and I changed the division from asset management and I got into the Watson. And one of the annotators that I worked on was IDF, Inverse Document Frequency, which had about that little bit work. Back then it was the UEMA pipeline, Unstructured Information Management Architecture, monolithic big Java code. Now it's microservices and Python, everything is written in that. And the machine, the big engine that actually won the Jeopardy game was SPSS. There was no neural network there. There was no RNNs and whatnot running. It was logistical regression. This is huge. AlphaGo, AlphaZero, Google bought them. What an amazing purchase. This is reinforcement learning. This is when they went up to Chinese authorities and said, hey, you have this game called Go game. There are as many moves in that game as there are grains of sand on earth. The white stones and black stones, and you have to capture the other with the other color. Don't leave a little stone empty because it can come out and go elsewhere. Well, the machine was never trained. This was not, that's reinforcement learning. It learned on the fly. An agent that gives it a thumbs up and a thumbs down. Yes, do that. No, don't do that. Project Debater is huge. It's huge. We are getting close to the Alan Turing test. Still some ways away, but in here we're using generative networks. Frankly, OpenAI, Elon Musk's company, has some of the best generative pipelines, adversarial pipelines. And we're using some of those to manufacture a sentence out of thin air, out of the ether. So the system goes back into its corpus. Yes, it gets something from Al Jazeera, and then it gets something from the CDC and another passage from the Der Spiegel. But the sentences in the middle, well, John, I see that you are trying to argue this point with me. Nobody typed that in the dialogue. The machine fabricates sentences in between conjoinings. Fascinating stuff. Now, this is one way that we're thinking about the evolution in terms of representations. 1980s, expert system. Notice there was a rules-based engine, an if then else. There was a corpus, and some inference engine gave some sort of a prediction. In the a few years later, these are single perceptrons mostly, support vector machines, decision trees, neural networks, task-specific handcrafted feature presentations. Fantastic. Deep networks came in. All of a sudden, now these are task-specific learned features. We don't manually adjust the features, but those weights, those hyperparameters is adjusted by the system. The backpropagation is one such way of going about it. And of course, ladies and gentlemen, foundational models. This is what we work with. Three research facilities, one in Almaden, California, the other one in Zurich, and the other one in Haifa, Israel. We are putting a lot of emphasis in giving the machine common sense, trying to give the machine world knowledge. You have a base. It is a jack of all trades, but master of none. From there, it becomes easier to build a doctor, a lawyer. Well, not one that replaces the doctor or lawyer, but a second opinion. That's our mindset. Mechanic for the hotel, concierge, suicide prevention, you name it. You know, the winner of the AI race, as we put it here at IBM, is not the country with the maximum information on their people. No. It's not the company or the university with the master algorithm. No. Although usually it comes from universities. It is the one entity, the one corporation, the team that was able to do maximum AI with minimum data. This morning, when I woke up, first thing I do is usually have my glass of water. I didn't even have my glass of water. My feet hadn't even touched the floor. I was waking up. And I had a hunch that this is going to be a great day. Well, good luck to the machine with that much data trying to predict that it would be a good day. That's where we want to get to. About cognitive systems. 4 things: understand, reason, learn, and interact. Cognitive systems, they need to understand like humans do. You know, when you build a chatbot, the brilliance, the intelligence of the chatbot is not in the answer that it's giving you. It's in understanding your colloquial way of speaking with the accent. You know, they trained Watson on my accent, just on the accent. It needs to understand what it is that we're saying. I don't want the machine to come back and say, I'm sorry, would you please repeat that? These systems, they need to reason. Concept expansion, for example. You know, I might be looking for document research on color blindness. Color blindness. 20 million documents come up. Google now actually answers the questions, doesn't even just give you a link. It gives you a darn good answer. There's this one researcher in Johannesburg, And she wrote her thesis, 450 pages, on the genetic mutation of the green and the red nodes in the back of the retina. Not once did she mention color. You just don't see the word color. Not once is the word blindness mentioned in this 450 pages. I might miss out on that document. I need a concept expansion to also bring that to my repertoire. Learning. They never stop learning, and this should not be a surprise. Look at us. We're still learning. We're still continuing to expand our horizons. People think, oh, I bought an AI system, I'm good now. No. You have to train this. Watson was a 0-year-old child. We got it to be a 2-year-old child. The APIs that we have now, which I will demo in a bit, they are already a 2-year-old child. The thing is already trained on the entirety of the Wikipedia. So we don't have to start from zero when we build a chatbot. And of course, interact. The Jeopardy game didn't interact. There was input and output. I want the machine to say, yeah, but. Are you sure about that? It needs to have an interaction to rebuttal, to debate my point of view. See how hard it is? Typically, there's a strong affinity between nose and smell. If I'm building n-gram, bigram, trigram in my NLP pipeline, I make a strong affiliation, strong connection. The saliency of the weights between nose and smell is really strong. Now, all of a sudden, the human comes in here and says, my nose is running and my feet smell. Well, the machine needs to understand. Slim chance is exactly the same as a fat chance. A wise man is so not the same as a wise guy. It's this is why we can't just translate from English to German. Spanish and French, they have male, female verbs. Chinese, Japanese, they're symbols. From the algorithm level up, it has to think in that grammar, in that construct. It's not just a matter of translating it. We want to make sense. This, ladies and gentlemen, is going to be child's play for you. Most of what I say in here for you would be like, yeah. But for my audience that I'm hoping might enjoy this in their 20s, who are aspiring to be masters of the universe, you guys are already there. This might be an interesting way to explain machine learning at its most plebeian level. Mesdames et messieurs, ladies and gentlemen, senores and senora, that is a hill. Hill. My job is to climb that hill. So they come up to me and they say, Armin, I need you to climb that hill. I'm like, oh, okay, no problem. I can do this. Oh, yeah, not so fast. I'm like, what? What do you mean? You have to do it blindfolded. Where's my Jamaican bandana? Boy, there it is. And you have to get there as minimum steps as possible. I'm like, okay, I can do this. I'm amongst friends. So they cover my eyes and I start going up. I notice it's a steep hill. Slope is learning rate. My eyes are closed. Machine learning is blind. I'm not seeing where the slope is changing. See, this is a different slope. This is a slightly different slope. This is a slightly different slope. The machine knows, or I would know that in here, the tangent of those coordinates, that's a tangent, or whatever it might be, is equal to 0. Remember sine, cosine, tangent. So I have reached a plateau. Either I go down or I go up from here. But because when I first started, my gait was really huge. So I go past it. Not optimized. Forward feed. Now I do a back propagation. Let's do this again. That didn't work out. So I start off on a smaller scale step. It's taking me 3 weeks to get up there. Not optimized. These steps are actually the weights, the hyperparameters. And when you start off on a machine learning project, typically you might go to NumPy and say randomly select a weight, a hyperparameter. From there on, I can adjust it. So when I first start, it's okay to have a wrong step. I'm going to do a back propagation, come back and redo it, back and forth, back and forth. That's why NVIDIA Corporation came up and said, you guys are still using CPUs? I think you need the GPU for this to do your math. The NVIDIA stock went up. Now, each company is building its own neuromorphic chips. The one in IBM is called North Star. It's a glob, actually. It's a blob. Germanium telluride. It's a phase shift. So the signal doesn't just go on a wafer. It can go up. It can go in the three-dimensional way. The gates now are at 7 nanometers. That's 2 atoms thick. The signal gets lost in silica. Really, really fascinating. The Moore's law is really being challenged now. So that's really, if I knew what the curvature changed, the slope, then my learning rate would get to slope. So all of a sudden, how do we calculate slope? Derivatives. And this typically might be a 3-dimensional setting. So I need to calculate the area under my curve. How do we calculate area under the curve? Those are integrals. So it's really interesting for me to reveal to my students how you would go from a statistical approach, good old logistical regression, to a part where you actually need to bring in a bit of a calculus. Let's continue. Slide show, play from current slide. Machine learning is blind. This is the simplest. I've seen some brutal formulas in the past 2-3 days. They most of them made me go woozy. This one is the simplest formula there is. Method of least squares. This is a machine prediction formula. I want this line to be a best representative of all these dots. Best representative. So I know what the y is. Tack, 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 tack. There it is. Thank you. Now, where is y hat? How can I calculate y hat? Well, y hat actually is calculated by mx plus b. B is my intersect to the y-axis. It could be 0 if it went to the bottom. It could be 0. M is my slope. I know what x is. What is my slope? Well, usually it's y2 minus y1 divided by x2 minus x1. Let's say that's the derivative. So as long as I can find out, now the trick in here, let me do a little Picasso for you. New slide, and perhaps a better looking color. Thank you. I shall succeed, I am confident. Format background. Thank you very much. So, back to our Picasso here. Let's say I have a distribution. Again, I apologize if this is boring a lot of the masters of the universe, but that's fine. It's again, my targeted audience of 20-something-year-old might find this interesting. Ooh, I also have an outlier in here. So my job is to come up with a line that really best, actually I don't want to use that line. Edit, undo. Design is good one. Insert is good one. Insert. So now all of a sudden, Felix is going to come and say, Armin, I don't think this is a really good representation. You see that outlier? We decided the outlier was a good thing. You actually need to move this a little bit like that. And then Howard would come and say, no. Not just that, you actually need to move the entire curve. Yes, both of them. So when we, typical multi-perceptron in here, the activity that takes place inside the hidden layer, that's the statistics. That's the logistical regression, ReLU, or parabolic tangent. This is what moves the whole curve. The activity that's taking place on the neuron, the sliding here, and on the, not the neuron, but really the synapse, is what's actually helping the slope to change. I have to be fair for all these dots that I have. I have to be fair for all those sections and segments that I have. You might say, well, what does take place in here? Lots of things. Back to my Picasso. Each layer might do a different bias detection. Bias moves the whole line, the curve, weights, changes the slope. Sure, we have an S curve. Right? You remember S curve. 1/1 plus e to the minus x. Anything to the minus x is same as writing 1/e to the x. That's an x. Or it could be parabolic tangent, perhaps. Maybe another layer would use this as a bias. The one that we use most often is ReLU, rectifiable linear unit. Comes in the middle and then straight line, linear unit. It could be sticky or whatnot. These are the various constructs, statistical constructs that lurk within these nodes, not neurons. That does injustice to what God created, nodes that help to make a better prediction. And of course, the weight that we assign to it arbitrarily is a randomly chosen number. 3. Good, bad, right, wrong, doesn't matter. When it goes through a whole bunch of back propagation, this might come back and be 2.9. Maybe that's all 2.978. Who knows? Again and again and again, until my prediction and my actual are starting to become closer and closer. Back to our regularly scheduled programming. This is interesting. So, you know, machine learning has, there's supervised, unsupervised reinforcement. Those are the most common ones. The reason I picked this particular slide is because it is a telltale sign of the sort of problems we're trying to solve with our quantum machine. It's really fascinating, the work that IBM is doing with quantum machine. It's not that we're replacing classical systems. You still need a classical system. But once you get into a quantum machine, the speed in which it can solve big problems. Some people say that quantum machine is a solution looking for problem. Well, simulating nature is one such challenge. Simulating the caffeine molecule is one such challenge. Understanding the protein for COVID, it's dead. It's a protein. You know, it's not the DNA, it's an RNA. How else might it mutate 6 months from now? So you almost need to model all the amino acids that go into that protein. How cool would it be for me to come up with a vaccine for a future variant that doesn't exist today? That's where we're using our quantum machine. Right in here. So, supervised learning, classification, regression. All right, classifications, identity fraud detection, image classification, customer retention, diagnostics. With regression, we can have weather forecasting, market forecasting, estimating life expectancy, Shor's algorithm, Grover's algorithm. These are the ones that come into play in trying to make that, help that prediction, especially when your hyperparameters are just endless, in billions, literally. And of course, then there's the unsupervised learning. Clustering is the favorite in unsupervised learning, and the type of challenges that a quantum machine algorithm, right now the algorithms for quantum machine are somewhat like the early days of, they're like Fortran, the early days. They do one thing and they do one thing good. Dimension reductionality, data visualization, for example, comes from that. Structure discovery, especially with biomedical engineering, meaningful compression, clustering, of course, recommender systems, targeted marketing, customer segmentation. These are really the sort of approaches that we want to introduce our quantum machine to be able to handle some of these amazingly broad and huge problems. This is an interesting one. First, there were websites, now apps, soon bots. Let me go back here. Our kids, let me see, would it be our kids? No, I think our kids. My boys are in their 20s now, so probably later on, maybe. But when they end up making me a grandfather, I'm ready. I'm telling you, I'm feeling it, but it's going to be a while, I think. They're going to say, yeah, they're going to come up and say, Papa, what's an app? I don't know what an app is. What do you mean download an app? Never heard of it. See, it comes to the point that, where's my phone? I left it in the other room. These are bots that are doing brokerages amongst themselves. The restaurant bot is working to the weather bot, is talking to the Gulfstream. I don't have to download Lyft, Uber, double authentication, put the credit card number in there. I just want to pick up my phone and say, get me a car. Oh, and reserve me a restaurant at the Chateau restaurant near the fireplace. Oh, and is the weather front moving in right now? Is the golf course open? I don't have anything installed really from any of these entities that they're API providers. This is the API economy. But there's a brokerage, there's bots that are doing the negotiation amongst themselves. Nothing downloaded, no apps. One-to-one versus one-to-many. This approach of yell and sell does not work anymore. I want chat and listen. Some years back, I was in the market for an automobile. So, you get a little bit more sensitive to car advertisements and this and that on TV. And they were like, come on down and buy a Toyota pickup truck. Everyone was saying that. I'm like, I don't want a Toyota pickup truck. I want my twin turbo V10. What do you mean a Toyota pickup? If you chatted and listened to me, I will come to your dealership and I would buy it from you. Small data versus big data. Bye-bye Hadoop. I want small data. I want chunkable, actionable small data that I can immediately, with that minimum information, make a maximum prediction. Always on versus always perfect, the real and the raw. My dears, you may remember some years ago, there was the Boston Marathon bombing. The way they found out those two brothers was actually they used neural networks. The cameras on Newberry Street, down here, on Newberry Street, they depicted humanoids, man, woman, white, black, doesn't matter, earthlings, looking that way eastward, with a bit more, perhaps definition, you might see august faces. But it doesn't matter. These aren't high-definition cameras at all. Some blah, 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 and there, two of those humanoids were looking this way, westward. Time series, LSTM, and those two other anomalies, they're outliers, they're anomalies, had something black in their back, and 2 streets later, they don't. The backpack. Oh, I don't know what they are, but it's an outlier. It's an anomaly. Is the video high definition HD 4K? No. But it is always on. That's what I want. I love this. Brute statistics versus artificial neural networks. So looking, comparing these two are really interesting. Regression takes the data and tries to find the result that minimizes prediction mistakes, maximizing goodness. And I want to make my line the best fit with all those dots that are scattered around it. No, regression, to regress, right? To look back. That's what regress is. Do you guys know this joke? No? Make sure I have enough time for my... I may want to start my demo quicker than I thought. A physician, an engineer, and a statistician, they go on a hunting trip. Here in Massachusetts, we don't have guns. We do bows and arrows. And so the physicist goes, I got this. Sees a deer up front. I got this. Calculates the curvature of the earth, the tension of the elastic. Goes, misses the deer by 5 meters to the left. The engineer says, no, man, you got to take the wind into consideration. Does one of these, calculates the wind, and says, I got this. Misses the deer by 5 feet to the right. This was left to the right. The statistician doesn't even bother to pick up the bow and arrow. Stands in the middle, goes, hurrah, we got it. Used to be fun. Being precisely perfect on average can mean being actually wrong each time. Regression can keep missing several feet to the left or to the right, even if it averages out to be the correct answer. Regression means never actually hitting the target. Unlike regression, machine learning predictions might be wrong on average, but when they miss, they don't miss by that much. Inventing a new machine learning involves proving it works better in practice. Inventing a regression improves that it works in theory. This one, you sit in the office, a CSV file comes to you, and you run some hypothesis on it. This one, you got to go outside, and you're going to feel the cold and the hot and the sun and the sweat and everything. Machine learning has less need to specify in advance what goes into the model and can accommodate the equivalent of much more complex models with many more interactions between variables. That's why now, no one's really coming up with a brand new algorithm. They're building up on existing algorithms. Capsule networks, for example, generative networks, adversarial networks. CNNs, you can't even use a CNN now due to the diminishing returns. Now there's RCNN, kind of has that feedback loop that recurrent neural networks has. By the way, I stole this from this book called Prediction Machines. This book is mandatory reading for my students in both of my colleges. So Wentworth Institute of Technology, WIT, here in Boston, and the other one is Monday nights. It's in Kentucky, the University of the Cumberlands. I'm a professor in both of those. Nighttime job, 3 jobs. Amazing book, amazing. Prediction Machines. You just love it, especially if you like economics. It has an economics flair to it. And now the demo. Watson Studio. Shall we do this, my dears? Let's begin. And I'm hoping we can do the because I want to come back and talk about our machines going to replace me. That's such a philosophical conversation. But I want you to see. Let's connect here. Our auto AI at work. There we go. This, ladies and gentlemen, if I was working in Microsoft, the name of this would be Azure. If I was working at Amazon, the name of this would be AWS. Google calls it Google Cloud. We call it IBM Cloud. It's funny, this 20 years I've been at IBM, I've seen the demise of the products and the rise of the APIs. Our tech sellers, all of a sudden, didn't know what to do. They used to go set up the 3-tier architecture, database in the basement, application server in the middle, the asset management application in the top floor. Now it's pay as you go. 20 cents. You click 20 cents. You have to become Lego builders and put these things together. Our catalog is where, I think of the catalog as the Mall of Dubai. I don't know if you've been to the Mall of Dubai. You can buy everything there. That's the catalog. And the ones that I am most familiar with, community storage, networking, containers, integration, boom, boom. These are my children. These 19 over here. I'm going to go in there. Watson Assistant. That's how you build a chatbot. Watson Studio is the one we're going to go in now. Watson Studio is more of an IDE, integrated development environment. It is friendly with all these other ones. You can bring them in. Structured, unstructured, and so forth. And Jupyter Notebooks, RStudio, model building, so forth. Well, it's lots of fun. And there's lots of good things. Speech to text, text to speech. OpenScale is about fairness. Was there bias in the algorithm or was there bias in the data? Why didn't you give loan to this person? Really, really interesting. So forth. All right, let's begin. I'm going to click Watson Studio. Many locations. I am closest to Dallas. I'll stay with Dallas. And I have read and I agree. This is free. So for universities and stuff, we have, you can access this for free. I don't want any errors, just a simple get this going. Thank you. I tell my students, if you see something blue, click it. Don't read. Do you see something blue here? Click it. Oh, it's provisioning it. In other words, it's building a NoSQL database. So I can bring in unstructured data. Provision, what's in there? No. I got this. I want a new one. Thank you very much. Projects, view all, new project. Thank you. New project, empty project. Thank you. We're going to give it a name. BICA 2022. Or, the data set we're going to work with is about loan fraud. Yeah. So I already had an object storage, so it's from the list. Fine, put that way. So really, this is what we're going to do. Told you about that. I'm going to go open up one of my projects in here, resource list. I bet you that's because I had it on for running for so long. It looks like my internet is also. By the way, can you guys hear me well? Is my voice becoming too? Look at all this reflection from here. It's a lot. Too much reflection from it. Can you hear me? Can you see me? Everything okay?
Yes, it's okay.
Yeah, okay. All right. Resource list, let's go to the dashboard. I was hoping for no surprises. I want no surprises. I have 72 of them. I'm going to open up my old Watson Studio that I had here. Wow. Let me put something in here to stop the reflection coming in. Table, crazy. Watson Studio, I'm seeing it. I was working with Anam the other day. We'll go there. See blue, you click it. Not yet. The project, empty project. Oh, this is a new one. I wonder if there's something right. Cloud object storage, yes. API docs. There's another idea. Cloud object storage. Thank you. I'm going to create a new one. What do you mean? And one more try. Let's see if I have one that's already running. Never fails. Each time on a nice new demo, it decides to do this thing. So if this give me another problem, I'm going to go back to our presentation. It's in Studio. The latest one, fundamentals, maybe that. Cancel. I'm going to open, see if this one. Assets. Okay, this is the one that I wanted to work with. Credit German risk. I used the one that I did a month ago. Looks like it's not yelling at me. Let me show it to you. So this is a typical bank, USB bank, UBS bank, and it's collected data. You know, what was the checking status of the person? How long was their loan duration, their credit history, loan purpose? What was the loan amount? Did they have existing amount, employment, so forth and so on? And interestingly, at the end, we have our training column. And I like it how it's not 1 and 0, risk, no risk. So this is training set. The answers are provided. Let's say this actually is from the Kaggle competitions, this particular German credit data bias training. They use it in Google competitions. It used also a lot with detecting bias and so forth. So we want to see which one of these kind of characteristics. We're not after people. This is not, you know, name, social security number is removed. What kind of a characteristic trait might lead someone not pay their loan back? All right. And well, I had the notebook in here. Let's create a new asset. I'm going to find connections, parameter setting, Jupyter Notebooks, SPSS, applies data replication. Data refinery, pipelines, parameters. So auto AI, all of a sudden, this, of course, it allows you to save it as a notebook, projects. Try one more loan file, see where's my auto AI. Data tab, new asset. Would be in pipelines? I don't think so, my dears. Alas, I couldn't get to show you the auto AI. It's such an amazing thing. That's welcome to live demos. I'm going to take you back to here. And once I get that, I think I have a demo on it. Actually, I can show you the demo exactly on it. If you go to LinkedIn, I have it on my LinkedIn. That's me. View. Alas, I don't have a few minutes to stop. And tell me if you got the answer right or wrong, based on the study that you did in classifier. One wasn't enough. Gradient boost. This book hasn't even checked. Gradient boost classifier. Light gradient boost. Just so yeah, I do speak colloquially in this video, but notice the system brings up its own algorithms. It decides. You can then save it as a Jupyter notebook and bring in your personal algorithm, but the system decides what it is that it wants to bring in. This was the same Excel spreadsheet that we were looking at. And no risk was the column that I selected as my x-axis. All the other ones were y-axis. This is the predictable column. Selected the algorithms, or let the machine go with what it reckons would be the best. You can have a number of pipelines. 2 means the machine will select 2 of these. 3, it means it will select, we don't tell it. It looks at the data set and says, I'm going to use random forest trees, logistical regression, and XGB classifier, extreme gradient booster. Fine. Looks like I picked 2 in this example. And then we say, okay, I want threefold. Test, train, and then you train it on a set. You hide maybe 10% of it. Here, we hit 10% of it and test on that one, supervised learning. And in here, you have an opportunity to maybe uncheck some things. Maybe there's it shows you all the columns. These are the same columns. It allows you under the data source to say, you know what, this says social security number. No. Address. No. Uncheck it. Telephone number. No. Uncheck it. This is a pretty cleansed data, so we used most of them. And then we click. We click really. It says there's no coding going on in here. And it starts to build with the 2 pipelines. It picked the gradient boosting in here. So it went through, read the data set, split, processing, and so forth. And one of the pipelines ends up getting the star. Becomes the winner. It's the one with the highest accuracy. So we select, we click in that one. It's continuing. Looks like this one now did better. And what we look at, I tell my students, know the confusion metrics. Know how to connect using the confusion metrics to calculate accuracy, recall, precision. True positive, false positive, true negative. These are the lingos that you hear a lot in our data science department. And this is a receivable operating curve. False positive is the x-axis, and true positive is the y-axis. This is giving me, it's like the F1 score. It's giving me how well advanced it is. And who knew? Loan amount, this is 0.999%. Age, loan duration, 59% possibility that somebody may not pay their loan back if loan duration is of concern. Age seems to be even higher. This new features it does feature engineering, adds and multiplies sine, cosine of checking status. That's 37% and so forth, and it goes down. Really, really fascinating. See how it does the trick for us. Google has something called Auto AI. They requires a little bit more command prompt. This one is really nicely UI driven. I ask my students to put in their own CSV file. Find a CSV file, us.gov, and come up with predictions. and that becomes their final project. Alas, I have very few minutes left, but I'm going to take it. Our machine's going to replace me. Slideshow, play from current slide. Human advantages over machines. Prediction relies on data. That means we have two advantages over machine. We know things that machines don't, world knowledge, not yet anyway. And we are better at decision making when there isn't much data. Ask Abraham Wald or me when I woke up this morning and I knew it was going to be a great day. I didn't know the demo would give me a bit of a conundrum here, but after 20 years of running demos, you kind of expect everything. Humans have three types of data that machines don't. Touch is coming. Runners are wearing these gloves, but as they get close to a different runner, or if they get close to a tree, it vibrates differently. Usually the blind runners, they run with a partner, with a coach. It's really interesting. Smell, well, if the machine, I'm sitting in here, I am so hungry, that's a great food coming from the kitchen. Can the machine do that? If it did, I would have a lab on it. We are the final arbitrators of our own preferences. This is huge. This is huge. Dear machine, thank you for your prediction. I will be the judge. You tell me it's going to rain tomorrow, but don't tell me to pick up my umbrella. I have this special hat that I'd like to wear. I'm going to wear that one. And the sun is reflecting like crazy from top of this table. We didn't know about that, did we? Was that a little bit better? Concern. Privacy concerns, they restrict the data available to machines. As long as enough people keep their sexual activity, financial situation, mental health status, and repugnant thoughts to themselves, the AI system will have insufficient data to predict behavior. And I stole that from this book. AI enables a partnership between human and machines. We excel at morals, imagination, compassion, judgment, and common sense. There's nothing common about common sense, I'm afraid. The machines are really good with pattern identification. It's the if then else that the machine is good with. I'm like, if I leave now, the traffic should be less. I should be able to pick up my sister by 4:30. That gives me 15 minutes to get to the flower shop. I might be late to pick up my dad. If then. But not the machine. Goes through a tree structure, comes up with the traveling salesman problem. That's where you need a quantum machine, the optimization. Comes up with the best route that I can do to pick up everyone and not be late. The machine does better than I do with my if-then else. This is a great story. I want to end with this story. Artificial narrow intelligence. That's where we are now. The best of self-driving car, Google. It really does one thing and one thing good. Now we call it artificial broad intelligence. You can have a bunch of narrow ones together. I'm waiting for the automobiles to communicate with one another. Right? I'm glad it's a level 2, level 3 autonomous driving car, but can you talk to the other car? Hey, I'm coming, watch out. This, mesdames et messieurs, meine Damen und Herren, Senores y Senioran, is the big thing. I have experienced that. I have experienced it. A rudimentary version of it, I will tell you. This is before COVID. Back then, we used to travel a lot. Back then, my travel points at the Hilton Hotel, I would come into the Hilton, they would say, Señor, IBM, por favor, pasar. Now they put me in the boiler room. I used to get the top corner, sit in the front of the plane. No more points, but that's okay. During that era, I was invited to Carnegie Mellon University, CMU, the robotics department. The first thing I did when I got there, I said, but I knew the tooling. If you're one page ahead, then it's not bad. So I was to run a workshop. I went into the robotics department, and the receptionist was a robot, not a humanoid robot. No, it had one lens in here. There was a screen up in here. The legs were just a pod, one pod, and tractor wheels. I went in, I'm like, hello. Hi, Armin, welcome. Facial recognition, had my bio, and it knew that, about my meetings, not hard concepts. Later on, they told me, had I gotten there early, would have asked if I wanted to go to the cafeteria for refreshments. But so I'm like, I have a meeting with John. Where's John's office? Sure, Armin, follow me. Okay, following the robot. It's going down with the tractor wheels. The pod is turning greener. I'm colorblind, red, green. I don't know what they're doing this, but I could tell it was changing color. So I'm following it. It went by the elevators, and one of these AI engineers, she kicks a chair in front of the machine. No facial expression, very stoic. Just kicks a chair in front of the machine. The machine stops. Easy. Laser, LIDAR, sonar, monar, it stops. No problem. I stopped also. Same thing. The machine goes around the chair, leaves the chair in front of the elevator. I did the same thing, left the chair there, looked at her, no emotions, nothing. I went around it. We got to the John's office. It's telling me 5 meter, we turn left, 3 meter, we turn right. Okay, good. We got to John's office. John asked the machine 2 questions. Hard for human, let alone for a machine. What happened at the elevator? Why were you late? Oh, it answered them. The machine is gaining experience. It's not just training. It's different. We're working on this in our Almaden research laboratories in California. It's called Embodied Cognition. Huge. ASI, it's not here yet. Quick example on the ASI. Today, I might ask Watson, can you tell me about black holes? And Watson might say, I'm sorry, Armin, I don't know about black holes. Perhaps you can teach me. I'm like, okay, eat this PDF and that website. Now it knows about black holes. On the day of ASI, it will know the black holes anyway, but the answer might be like this. Watson, can you tell me about black holes? I'm sorry, Armin, I know that I don't know about black holes. Self-awareness. This is when they get together, they move to a community, they elect a representative, they come into the city in the daytime, clean the streets. There's no automobiles. There's no parking lots. There's no car insurance. There's no speeding ticket. There's no meters. They take us, they move us from here to there. There's no front or back to these pods. They come and clean the house, cook the food. Some of them stay back at night to do policing. And they go back to their own section. This is my last slide. AGI, this is according to Ray Kurzweil. He's at Google now. He founded an amazing university, the University of Singularity in San Jose, in NASA Ames Research Laboratories. I went there twice. Amazing. First of all, you have to get through 20 gates and 5 IDs, and then you go into NASA research area. There's so many startup companies that have to do with space. I love space. And all of a sudden, there's this building, Singularity University. In the back, you can see a big hangar, you know, like the Zeppelin ship, that airships. It's for that. It's for testing airships. Google has rented that now. They're using it. The classes start at, what time did they started? They started at 10 a.m. and they finished at 10 p.m., 6 days a week, 10 months, master's degree. 83 students there, 2 of them were from America. Government had sent them from Uzbekistan, Tajikistan, from really on everywhere. And their mandate is to solve a world problem. quote a thing, the food in the cafeteria. I'm like, what is this? He's like, yeah, we feed the brain. So anyway, Ray Kurzweil is the one that made this prediction, who created that university. 2040, will I be here 2040? Yeah, I think I'll see this. I'll probably bug out over here. Happy to say I won't be here for that. And that would be very, very interesting. Mesdames et messieurs, I'm so sorry the demo was giving me hard times, but I was able to at least show you somewhat from that YouTube how Auto AI worked. 9 minutes past the hour. Any thoughts, comments, questions?
Sorry. Now, we have not much time, so if someone has some question, please raise your hand. I can see. Okay, here the audience has a question. No? Okay.
Did you enjoy it? Did you get something out of it, or did you want to?
Was okay. It was great, your presentation. I have a question. In resume, what do you think about the interaction between human and cognitive computers, cognitive machines?
We hope, we trust that the cognitive machines will be a second opinion to the humans in every facet. We don't want it to be a lawyer, but it wanted to be the library that would find out for the actual lawyer what case happened in 1974 that he didn't know about that he can use here. We want the cognitive system to be a second opinion to the doctor. You know, after a while, if you look in here, I'm like, doctor, is this cancer or okay? Well, let me take a picture of it. And if the machine has gained the trust of the doctor over the years, and with 97% says this is a sunspot, it's benign, it's not cancer. So the doctor can go and then maybe just take a little biopsy. I don't have to go through surgery and all this to recover. Sorry, sir, we didn't have to do surgery. That little bump in here was nothing. Couldn't you have determined earlier and made this easier instead of all that? So we're looking at cognitive systems as machines that can do really good prediction with minimum data. I don't want to spend months training this. Minimum data. Don't give me 50 pictures, 2 pictures, and I wanted to know that this is the same guy. And that's really the mindset we have for cognitive systems now.
Okay, and now that you are talking about prediction and small sets, don't you think that the way we are working with computers is missing something? Because we as humans, we make decisions with the very, very small sets of data. So it's rather something that to know how to choose the right set of data, the right set of parameters or something like that. Because the amount of computation that we need today to make a computer cognitive is huge. So what do you think about that?
Such a wonderful question. Yes, it's, you know, how can you say minimum data? A machine needs data. It needs food for it to predict. And you want to give it 2 pictures and have the same thing. That's the plan is to work on that foundational level now. It's the next level in artificial intelligence, where you have capsule networks, generative and adversarial networks, coming to bear and giving the system common sense, if you would. Once you have that as a base platform for all cognitive systems, now you start to sell the product, not before it. Now you go to the hospital and say, it's easy. I can make this a doctor in 2 days because it already knows a lot of things. So for that minimum data to become a realization, the machine needs to already start from a maestro level with a base, broad, general world knowledge. Not a master of universe, but also not a 2-year-old either. Once you get that into place, then it's much easier to give the machine 2 pictures of me and say, who's that third picture? And with a 97% confidence to say it's the same guy, not 64% confidence. Felix, did I answer the question at all? Or?
Yes, I think I have another question. Don't you think that the level of abstraction that we are using in computer is very low? So they need to make a lot of processing to answer or to give an answer to all requirements. And that I'm not sure. What do you think about the meaning or the level of abstraction that we are using in computers? I think in computers, in a cognitive system, we are using knowledge, not data.
Cloud machine data, you said?
Yeah. Cognitive information. We have knowledge, nor just data. That's why we are doing the computers make a lot of processing. Because we are still far from a cognitive system. We are still very, very far. We don't know how to determine a context that is essential to try to solve a specific problem. And it means that we are not dealing with the correct information, or we are dealing in different level of abstractions. So what do you think about that?
Yes, that is a elusive problem that's haunting all AI systems. That hasn't gone away. There is a possibility that if I can get a quantum machine to work with a classical machine, then I can actually bring in 1 billion parameters. That's past human level of abstraction. But I need that, what the human does, in a picosecond. I can come up with some sort of an abstraction based on very paltry information, not the machine. But if the machine can take the hand of a quantum system, now it gets close to where I am. And that's where I want the machine to be, to lead to that level of confidence based on such a paltry level of abstraction that almost it had to put together, and I couldn't even give it. So it is a ways to go. It is ways to go to get to that level, but we are seeing advances. There was danger of a third winter of AI, and guess who saved us? Elon Musk with OpenAI. The algorithms over there were the ones that basically averted the generatives and the discriminators. We're the ones that were able to give a new life to cognitive computing.
Okay, thank you very much, Armin, and thank you very much for your talk. And I think we ought to continue. It will be a pleasure to continue talking about this fascinating area of research. Thank you very much. Okay, thank you. And now we ought to continue with our program. So please, Alex.
Good day. My name is Alex Sanchez. I will be the chairman during this presentation block, which will start with Vladimir's presentation. Vladimir, are you ready?
Who? I'm sorry.
Vladimir Zulego.
Vladimir Zulego. Oh, I'm sorry.
With the work on the possibility of ontology map constructing on the cerebral cortex.
Yes, I'm here. I'm ready.
Share your presentation, please.
I'm here. And I can switch my presentation. And just a moment.
Okay, you have 15 minutes to present your work, followed by 5 minutes of questions from the audience.
Again, please, how many minutes I have?
15 minutes.
15. Okay, I will try to be very short. I want to talk about the possibility to make an ontology map on the cerebral cortex. It's I will tell about the one way how to make it. We formulate the hypothesis. This has been put forward about the possibility of setting up an experiment to test the correlation between the factorial mathematical model on the subject area and the thinking model of the subject area on the cerebral cortex by analogy with the semantic map on the cerebral cortex. It is proposed to build an ontology map on the cerebral cortex and so localize the thoughts on the cortex. A number of arguments are given in favor of such a hypothesis, and the possibilities of setting up an experiment are discussed. According to the Web of Science, since 2009, the number of publications in this field has surpassed the number of publications in such fields of physics such as physics and chemistry. And many countries started the special program to investigate the brain activity and to make a model and include Russia. Here has been adopted some program which concerns this problem. I suppose that the problem of proposed for discussion in the paper lies precisely in the field of the study of conscious and modeling of thinking. I suppose maybe I will pass some of this text and we'll start immediately from the key idea because I have enough short time and hope it will help enough to talk about all of my ideas. The key idea arose in the intersection of research of modeling brain activity based on the dynamic nonlinear equation, which was in the Chernovsky group in Russia, and a particular task on the modeling complex hierarchical system of the subject area based in the interaction matrix, which my group studied some years ago. In order to understand the idea, we will briefly outline the essence of the method of constructing mathematical models of hierarchical system based on the interaction matrix. Suppose that a group of experts is given the task to build a model of some complex static system that can be decomposed into subsystem. The last in turn are likely to be simply but non-composite. The system under study is considered to be quite complex, and the identified subsystem always turn out to be interdependent on each other. Such a system was developed. The algorithm to investigate such a system was developed in a Society articles and his group, and his approach can be briefly formulated as consisted of 3 stages. The first step is the identification and allocation of subsystem and the subsequent clustering of the subsystem in the global system. Second step is to determine the degree of influence of subsystems on each other, as well as calculation of the connectivity of this subsystem, calculation of influence coefficients, construction of the matrix of mutual influence. Very important idea of to use for this tasks matrix of mutual influence. The third step is the establishment of the hierarchy of subsystems. And later in our group, we developed the similar method for dynamic system. It means that we take into account the dependence of such subsystems on the time. And when we investigate the influence subsystem on each other, we take into account the dependence of these coefficients from the time. And so we establish new algorithm, differs from the CITES algorithm, a few essential points. In particular, the survey expert is conducted according to the special rules. First rules is each subsystem must be correspond to an essential factor, we say, and which are described by the function. It means that such a subsystems could be explained and correlate with such a function. Secondly, the question of the influence of factors are set in such a way that allows you to obtain from the expert survey. There is actually a knowledge of the ratio. You see this ratio. Namely, experts are asked to the following question: to what extent will be the increment of the factorial function xi cause a change in the factorial function xk? Simply put, in the language of fractional function, this substantial function, it is necessary to answer the question: what is the ratio of this such change? And next, what will be the direction of such a change? Change of the factorial function xk caused by the change of the factorial function xi will be in the same direction or opposite. This matrix takes into account the dynamics of the system over the time that makes it an interaction matrix, in the contrast to the matrix of mutual influence which used in CITES algorithm. Since the relations found in the survey determine the relative magnitude and sign of increments of one factor function depending on another, and allow us to construct a mathematical model of the interaction factor in the system. So how we will build an interaction matrix? This short algorithm, how we do to get this interaction matrix. We start from the point that we just find out the general depend on the other fractional function. Each function depends on others, and this functional dependence we can write in this form. Number one, expression number one. It is a classical form of equation when modeling the dynamics of hierarchical system in the language of fractional function. If the form of the function were given, then the description of the system dynamics would be a very simple task, and which would be solved either by exact solution of equation 1 or by the numerical integration. However, the exact form of the functional FK, which determine the interdependence of the factors, almost never can be established in exact form. Note that the so-called living system or echo-like system are characterized by the fact that they have a so-called asymptotic or stationary solution. We will use this fact because it is important for further algorithm. If we expand the function, original function, into a Taylor series near these values, then instead of system 1, we can obtain with the appropriate change of variables an approximate system. Number 2, it's approximate this non-linear global system. Practically all known models of complex hierarchical system can be reduced to this type. Thus, instead of an exact solution, we can obtain an approximate solution too, in the neighborhood of the asymptotic. What is the benefit of equation 2 compared with 1? The fact is that some of the coefficients in system 2 can be determined from the interaction matrix. In particular, this matrix D numbers will be just the numbers from the interaction matrix that expert determine. The remaining coefficients can be determined from the requirement of the correct behavior of the equation for asymptotic values of variables. We introduce notation to the matrix. Next, we introduce notation for the matrix B. And this picture shows how we determine this matrix. This matrix contains the diagonal elements. We call these elements as a self-action, and it is non-linear part of this non-linear system, equation system. And the off-diagonal elements are obtained from the expert surveys as a ratio of quantities. This the derivatives of the fractional function. And this matrix, and it is this matrix that we will call the interaction matrix. So we, using this denotation, we can write the system 2 for the global dynamic system can be represented in the form 3. The equation constructed in this way is much easier to analyze than the exact equation 1 and can be calculated numerically in all particular interesting cases. Thus, unlike Satie algorithm, a fourth stage is added to his algorithm, the stage building and dynamic model. And this stage could be named as a mathematical modeling of the system in the form of a system of non-linear equation using quantitative characteristics obtained as a result of analyzing and survey of expert. We can call this equations number 3 as a hybrid model because it is obtained from the exact equation 1 by decomposing near the asymptotic and substituting non-diagonal numerical coefficients from the expert surveys. This equation contains the a sort of expert panel intellect. In practical tasks, this system is extremely useful.
1 minute left.
Sorry?
1 minute left. You just want 1 minute.
Not clear.
You have 1 minute left.
Okay. Finally, just I wrote down here some additional index which can be useful to analyze the system, include those metrics which I wrote down up, and those index very useful to classify the system and to analyze how strong this subsystem influence on each other and how we can clearly clusterize these subsystems. And finally, what I will tell about what the reason we have to wait for new result in the proposed experiments. Experts are invited to compare and give their assessment of the degree of influence of the one factor to another and the reverse influence. Subsystems associated with this factor are compared, which may consist of components, substructures, and represent complex objects and are in many connections with each other. They are not words and not just concept. They are essence or higher level, and we can call it the thoughts. The whole construction 3 is a forecast of the behavioral factors encrypted into the account and algorithm. In such a system 3 is simulated by neurons, then this forecast for the subject unfolds into an understanding of the situation. Then the whole structure 3 could be called as a cognitome, since it contains understanding of the described system and it is carrier in the same time. Expert given us as assessment of a direct and reverse pairwise influence in the form of numbers and the sign of influence direction. Therefore, we can try to find correlation with the signals on the cortex, not only by the fact of the events, one pulse, but also by the magnitude of the signal, so 2 numbers are called in a survey. And since 2 factors are being compared in the survey, the neural activity of the brain should be manifested in the areas corresponding to the 2 factors being compared. There should also be some asymmetry when they answering a direct and reverse question. It is also necessary to analyze the allocation of responses on the time scale, which can give an indication of which of the recorded signals can be associated with the factors being compared. This work, and finally, this work was supported in part by Ministry of Science of Higher Education of the Russia Federation, this number of projects. So, thanks for the attention. So if somebody have a question, I'm ready to.
Well, now we will proceed with the questions. If anyone has a question, please raise your hand. Okay, no questions.
Yeah.
Well, we will continue with the work by Alexei Santanovich. The work is Physiologically Inspired Cognitive Systems. Alexei, are you ready?
Yes.
Can
you see my screen?
Yes, I can see.
All right. So this will be a cumulative talk for several of my presentations. And I will also talk in general about the field. So let me start with the following picture. When I published a paper 10 years ago about the BICA challenge, I identified several problems that are still unresolved, and some of them are partially solved, but altogether they are necessary to solve the challenge, which is to create a functional equivalent of the human mind. Looking at this set today, I can name the following problems that can be divided into easy or relatively easy and difficult, as always in AI. This reminds the history of AI in general, and now it is about the BICA challenge, which is the challenge to create a real-life computational equivalent of the human mind, capturing its highest cognitive functionality using solutions inspired by the brain. So it turns out that sensory perceptions such as vision, audition, turned out to be relatively easy, with, of course, some problems that remain unresolved now. So relatively easy was text processing without really understanding the text, as well as speech generation. Generation of expressive behavior, including expression of emotions, that was also an easy problem to solve. Classical fields like problem-solving, planning, logical reasoning, decision-making, imagery, general knowledge representation. That's all parts of the classical AI that mostly belong to the previous century, as well as simple theory of mind or representation of simple emotions, unlike complex emotions that we still do not know how to represent. Among the difficult problems are such things as context understanding, common sense reasoning, goal setting, creativity and insight, emotional intelligence, especially understanding of emotions themselves when it comes to social or complex emotions, generation of social behavior, self-awareness and self-regulation. Particularly difficult is the problem of defining tests and metrics for human likeness of artificial intelligence, whereas tests and metrics for humans is an easy problem. Okay, so I would like to now talk about several selected problems from this list, and I will start with the problem of complex emotions. We all heard the very nice informative talk of Antonio Lietra, who developed a model of complex emotions as combinations of simple emotions represented here on the several models. They all converge basically to the same. But my opinion is that it is not sufficient to have just dyads of simple emotions to represent complex emotions. And this is why we developed this concept of moral schemas that actually reflect relationships among the agents and represent social relationships. And the idea of a moral schema is that you have some sort of a normal condition which must be achieved and maintained. And that normal condition is represented by the set of feelings. So I'm not going to describe all the details of the theory because I do not have time for this. I just want to say that we have several projects based on this theory implemented in simulations of virtual reality and explored in human subject experiments. And these are virtual register, virtual poster presenters, as you see here, virtual PET, virtual convention center. You see a screenshot at the bottom with John Laird among participants in our conference, a virtual partner dance, and so on. In general, this approach involves a combination of 5 directions of research, one of which design of the paradigms and the implementation of them in platforms such as virtual reality, virtual environment, extended reality, as well as robotic platforms. We are starting using them too. Another set of problems involves multimodal interface that enables emotional communications between the human and the artificial agent, including facial expression, gaze, voice, speech, gesture, body language, actions, so on. Then we have 2 kinds of models that control the agent behavior, the cognitive models and neural network models, or should I say cognitive symbolic models and neural network models. And finally, the problem of tests and metrics, which I am going to briefly discuss now on the example of our project called Psychometer. And let's start with the question, would it be possible to conduct psychological testing of a person during ordinary conversation like registration in a hotel or buying airline tickets and so on? And if yes, how this can be done with an artificial agent? So we took this challenge, and the study was organized as follows. We had subjects, human subjects, performing psychological tests like Big 5, and we had the same subjects participating in the interaction with the virtual registrar, where they had a simple conversation and their choice of answers was recorded. So this is the list of questions and answers. This is the example of the dialogue. And let me show you briefly how it looks when the subject takes this test in virtual reality. On the left is what the subject sees, on the right is the real room. So what turns out is that, yes, the model was controlled by this BICA cognitive architecture that, again, I do not have time to describe. So when we did the analysis of responses, actually in this case we had responses collected in SurveyMonkey, just in parallel with that experiment. And it turned out that there is a very strong correlation, if not a quasi-linear dependence between results of psychological tests and results of behavior logging in this experiment, which means that indeed we can record and obtain characteristics of the subject personality and possibly emotional state during this simple conversation. And the next challenge is, of course, to do it dynamically in a free, open scenario of a conversation with the realistic agent. And by the way, the reason why I'm talking about it here is that the same method can be used for artifacts. If we can establish a connection between behavioral pattern and psychological type of person, then we can measure the psychological type of a virtual agent, and that will give us the direct answer to the question how human-like it is and what's the distance to the goal. And once we have this distance, the goal can be achieved. The next topic that I would like to address briefly is modeling of insight and creativity, and this is the work that was done together with Vladimir Redko. The insight phenomenon is generally characterized by a situation when there is a certain problem, like in this case, connecting the two ropes hanging from the ceiling, and the solution does not come into mind immediately. Then the problem goes into subconsciousness for a while, and then there is a sudden feeling of enlightenment followed by awareness about an idea of solution. I'm sure that you all had this experience in your life. And finally, there is an elaboration of the idea that leads to a valid solution. It turns out that this phenomenon can be described with a model based on the dual process theory, including system 1 and system 2. Let's say it could be called working memory and long-term memory, or consciousness and subconsciousness. And so we have one system that elaborates the solution, reasoning about it logically, and builds the solution as a chain of connections between schemas, let's say, in this case. At the same time, there is a massive parallel processing going on. I'm sorry, this should be system 2, and this should be system 1, or vice versa. So there is massive processing going on in system 1 when we have candidate solutions popping up, and they need to be tried. So when this happens, the system will send a signal to system 2 that possibly a solution is found. So in general, we have 4 possibilities of this scenario, like aha moment when the search requested by system 2 was successful in system 1 and the solution was found. That's not an insight yet. Another is the feeling of insight that opens the mind in system 2 and makes it listen to candidate proposal from system 1, which then turns into an idea that leads to a solution. Or there could be false insight when this process does not lead to a solution. And finally, there may be a latent insight when the moment is lost and the solution did not come in time. So actually, all these 4 possibilities can be modeled with the model that I briefly described, and we did some simulations. And maybe this is the way to build insightful, creative AI. We shall see. Finally, I would like to entertain briefly a more general idea, which is a combination of deep learning with evolutionary computation. Why do this? It seems crazy because to do deep learning, you need a tremendous computer power, and to do evolutionary computation, you may need even bigger computer power. So connecting the two, you would multiply the necessary power requirement, and which makes the problem absolutely not solvable. Well, my opinion is that every problem can be simplified to a way that it becomes solvable virtually on any computer. And so why do this again? Because just think of it that all cognitive models are designed based on algorithms, need human labor, and it's all done by hands, whereas neural networks are learning themselves, like they only need data to learn. So one possibility is that they can learn from data generated by cognitive models, or they can learn from each other examples of behavior. And in this case, it becomes an evolutionary scheme. So actually, in this diagram, which I again do not have time to describe in detail, there are several steps of this evolutionary scheme, during the first of which neural networks are learning how to behave from the cognitive model behavior. Then they start evolving themselves according to a genetic algorithm scheme in which the role of mutation is played by learning, by teaching one network, teaching by another network, and the recombination would be the case when one neural network learns from two neural networks, which means the functionality that develops inside that network would be some kind of combination of the two functionalities. And the role of the fitness function is determined originally, again, by the cognitive model. Later on, this role will be taken over by neural networks that will become judges. So that there is a co-evolution of two populations of neural networks. And finally, we might have a solution that will substantially exceed the level originally present in those cognitive architectures without human labor, without manual engineering, and so on. And that's also interesting because it seems like the beginning of a real artificial life, when things start evolving by themselves, developing by themselves, not requiring human participation at every step. Okay, I will finish here. Thank you, and I would be happy to discuss your questions. By the way, this title of my talk is also the the title of the special issue of the journal that is just open, and you all are welcome to submit papers to it. Thank you.
Thank you, Alexei. Now we will proceed with the question from the audience. If anyone has any question, please raise your hand. Okay, no questions. So we'll now proceed with the next presentation. Thank you, Alexei.
Okay, you're welcome.
The next presentation was presented by Irina. The work is The Maze Runner: Navigation Through Basic Kinetics to AI Models of Human Metabolism Pathology. Irina, are you ready? Is there any other author for this paper present? Irina Tokukin. Pregunta, ¿no? Irina Tokukina, are you here? Or any other author from this paper? We wait 5 minutes, then we will continue with the next presentation. Okay, this concludes the presentation of this blog. Thanks to all presenters and to all the members of the audience. Ulysses will continue with the presentation of the next blocks. Thank you.
Hello, good morning, good night on the other side. My name is Adrian Gonzalez, and I will be the presenter for this blog. Well, welcome. Thank you for coming to all the ones that are here. And for the first presentation of this blog, we have Irina Malanchuk with Cognitive Mechanism of Temporal, Transpective, and Dynamics of Natural Cognitive Architectures Providing Speech Communication. Is Irina here? Irina or any of their co-authors? Well, we'll wait for 5 minutes, see if she can make it. Otherwise, we'll continue with Lynn Renusau.
No. Raymond's ball. It's invited song. No. But it's only 11:20, so it's not this time. Lynn Remezal is here. Okay. I saw. Lynn. Oh, Lynn's here. Yep. Should I say hi? That Irina couldn't make it, so maybe Lynn has to start earlier.
Because at 1 o'clock we have this the last one.
Well, since Irina doesn't seem to be present, if Lynn is ready, Lynn as well, are you there? Yeah. Lynn, can you hear us?
No, Tancho tiene otra cosa.
By 11:40. He's also here. It seems that everybody's here, but we'll probably need to go out for a
Coffee or something.
I cannot see.
Yeah, it's here. It's the arrow.
But since they since they because
Hi again, just checking in if Lynn Rummelswall is available, maybe so we could start earlier and then they could have more time for the presentation. The presentation is First Step AI, a case study of a client application of AI. If the author, the presenter of that presentation is in the audience.
Probably not in front of this concept.
Tengo que apretar.
Yeah,
it's not. Yeah, he doesn't want people.
It's the time for going to the restroom and preparing himself. When you go to conference and try to solve I have spent very long journey.
Yeah.
No, it's a leading dependent valve, which is asking.
Hello, everyone. Since Irina Malenchuk does not seem to be here, and Lynn Remoswal, the next presenter, seems to be ready, we will proceed. They will present, Lynn Remoswal will present First Step AI, a case study of a client application of AI. Lynn, can you hear us?
I can, loud and clear.
Okay. Can you share your screen? Oh, thank you very much.
Just started. Can you see that?
Yes, we can see perfectly fine. Are you ready to present?
I am, yes.
Well, welcome and have at it, please.
Thank you very much. Good day, everyone. My name is Lane Remelswal. I've previously published in the BICA conference in 2020, and it's a pleasure to be invited back to give a case study talk about Cape Ray, a medical application of artificial intelligence. Before I start, can I just see how many people are in the audience? I see there's 15 people on the Zoom call. Can I get a sense of how many people are in the room in person?
We have about 8 people here.
Wonderful. All right. Well, thank you everybody for joining. It's a great opportunity to give a real world case study, and I'm glad to have been invited to give this. My background is machine learning. I'm a PhD candidate at the moment, and I'm also a machine learning consultant for a company called firststep.ai. And I'm going to be talking a little bit about that case study, the problem that Cape Ray had and how we were able to provide them with a solution. Looking forward to engaging with the audience if there's any questions. And yeah, without any further, let me jump right in. To give a little bit of a background on Cape Ray. Cape Ray is a technology company. They produce both hardware and software. They're based in South Africa, on the other side of the world. And they produce a number of different machines, including this one here called the Akeso, right? Akeso. And they specialize in digital mammography. So X-rays and ultrasound. It's a combined X-ray and ultrasound in one device. So it's quite a unique device. And they take medical images of the breast. In terms of how they take that image, they take slices of images as their scanner goes across from left to right. And so you get both the width and the depth, and they take 235 slices, each 1 millimeter apart. So that's what we're dealing with here. And just to give you an idea of what that looks like once you try to recreate it in a three-dimensional form. So you can see there is the shape of the breast on the plate. There's a top plate and a bottom plate, which kind of squashes it in order to let the ultrasound do what it needs to do. And it takes slices, as you can see in this visualization. And in order to really dive into how we applied machine learning, I'm going to take a single slice. I'm going to talk about that single slice. So that's what we're looking at here. It's a single slice, a cross-section of that three-dimensional representation. All right, so let me take a little bit of time just orientating you around this, because this is really the problem that was presented and the problem we try to solve and we managed to solve with artificial intelligence. So what you'll see here is there's quite a lot happening on the screen. Most of this is actually noise and echo. With the ultrasound, the tricky thing is that ultrasound works well if there are solids or liquids. As soon as it reaches air, and there's any exposure to air, you start getting strange echoes. So if we have a look at this image here, what I've highlighted in green is the actual breast tissue that the client wanted to capture. You can see right at the top of the image, this is the scanning plate. It's a fixed width across. There's a few millimeters of plate. Everything on the right-hand side here is an echo that is created by the fact that there was air. And as a result, you have this echo that permeates through from all the way across the image. At the top of the breast here as well, you'll see that there's an additional echo, and everything outside of that green area is what the client wanted to remove from the image, because they wanted to hand this image across to a medical technician, and that medical technician wanted to do some evaluation on it, but all this noise was getting in the way, which is an interesting application for medical AI, because quite often medical AI is considered a diagnostic tool where you give it an image and it tells you what is wrong with the image or what the diagnosis is. In this case, we were asked to apply AI to clean up the image to allow the technician to make a more informed decision. So that is the context here. So you can see there's quite a lot happening. We've got echoes on the right-hand side. We've got dead space at the bottom. And we've also got some echoes that come into the middle of the image, which they wanted to remove. So it's quite a complex problem. And what we then used in this case was the FirstStep.ai design tool. So FirstStep.ai, they provide a fantastic design tool. In short, what you can do is it focuses on visual AI. You upload your data set, you can do some annotations, you can train your model, and you can then deploy it or process images using that model. And the really nice thing about it is it's leveraging all of this great AI technology, but it provides it in a no-code environment, and it's designed for non-developers. So there's a really nice wrapping around it that makes it really easy for non-developers to access it and get quick results. We were able to, well, currently we're able to deploy POC models to various different clients in a matter of 2 or 3 hours from start to finish. To give you an idea of the sort of AI that we have in terms of the toolkit and what we had to choose from to try to solve this problem, we had a range of image classification, object detection, object segmentation, pose estimation, 3D reconstruction, and time series forecasting. These are the tools that we had at our disposal. If we then have a look at what each of these are, I know we've got quite a lot of AI experts in the audience, so I apologize if this is something that is very familiar to everyone. And I've been listening to the talks for the last few hours as well, and I can see there's a lot of interest in different types of AI. But to give you an idea of how image classification, detection, and segmentation apply to medical imaging, Here's another example from another client where we have a fetal scan. In image classification, image classification would allow you to look at that image and tell you whether there was a fetus there or not, whether this person is pregnant or not. So it's more of a yes/no, applying AI to the entire image. Object detection is one step further. It identifies with a bounding box where in the image the object of interest is. Taking it a step further, even more complex, you get object segmentation, which quite simply creates a polygon around the object of interest so that you're able to analyze the shape, size, characteristics of that object. So these are the tools very easily we had available to us. And in this case, we're trying to solve this client's problem. We chose to use object segmentation because we really wanted to get down, not just whether something was there, whether there was echoes, but actually trying to isolate those individual echoes. So of the suite of tools we had, we chose object segmentation. We uploaded a number of images. I think we used about 50 images for this, a very small data set. It's got incredible results. What we then did was use the first step design tool to simply annotate using the object segmentation annotation tool. Very easy. You can zoom in and out. You can click and it automatically saves. You just switch across to the next image. And instead of doing this in a third-party tool and uploading the results, all of this is just built in. We then have a wonderful, well, the first step designer has a wonderful one-click training mechanism. You can literally click a single button and it does all the training for you. It tries to calculate what the optimal augmentation should be, all the fine-tuning, as well as what your base parameter or your base model should be. And I'll dive a little bit more detail into the base model just now and how that works. But for this case, a PyTorch model was chosen and used a combination of faster RCNN and mask RCNN to do the detection and the segmentation. Okay, what exactly is happening? And so most of you in the audience are probably quite aware of how convolutional neural networks work, but I've got 3 slides here. I just wanted to touch on it for those of you who aren't quite sure how it works and why they're so powerful. What a CNN does is it takes an image, I'm talking about visual CNNs over here, or image CNNs. It has multiple layers inside the CNN. And what it effectively does is it starts building up that image slowly. The first layer is a level of feature extraction. So it identifies smaller features within the image, everything from a line to a curve to a dark area, colors, and it combines those features at the next level called the classification level. And combinations of smaller features result in larger objects. So it starts to build up a concept from small features. So in this case here, take the sum of the small features, and the sum of the small features combined will be considered a motorbike. So there's a feature extraction layer and the classification layer. The really nice thing about CNNs is you can use something called transfer learning, meaning that you can start with a pre-trained CNN. And with object detection, I think this is an object detection screenshot, but you can choose from lots of different base CNNs that have been pre-trained on dozens of millions of images. And a pre-trained model applied to an image can give you something like I've shown you on the right-hand side here. You can identify cars, people, trees, a number of standard objects. To give you an idea of the COCO trained models, COCO is its data set with 90 labels, 90. So it's trained across 90 different objects, common objects, everything from a beer bottle to a tree, to a person, to a car, common objects that you would see. And there are lots of other different types of models as well that you can choose from. And why transfer learning is so important is because you start with a base model and all those features that have already been built into that model, that have been trained, it knows what a corner looks like, it knows what a circle looks like, it knows what a dark area looks like, and broken it down into features, those are preserved. It's only the classification layer which is retrained, meaning that sums of features in different combinations, you can then choose what to label that. So in this case, we've used a PyTorch model to solve this particular object segmentation model or some object segmentation problem. And the base model had been pre-trained on medical images. And we said, we are interested in echoes. And that is what we used and retrained in the classification layer. So after choosing that, it quite literally is a one-click training. And in the first step designer, these just pop up underneath each other, some of them quicker, some of them a bit slower. You can see the results, you can see the framework used, you can see how many epochs it ran. At the end here, if you want to dive in and you want to write or dive into exactly what's happening underneath the hood, you can click on it and you can get more detail about what is actually happening in terms of the loss, the MAP scores. So if you want to dive in and really understand why the best model was chosen and when it was chosen, there is that option as well. So it's designed for non-developers, but developers do get insight into what's happening underneath the hood with this toolkit. At the end, you then choose how you want to deploy your model. Do you want to deploy your object detection, object segmentation model on a mobile app? Do you want to deploy it to an edge IoT device? Or do you want to deploy it to a cloud server? And this particular client chose a cloud server. They process these images. So let's have a look at what's happening. These are the results. This is what we all want to see. How well did we do with identifying echoes using object segmentation? This is the image right at the beginning, the before image. Object segmentation successfully managed to remove or identify. We were then able to remove. So it identified the echoes very comfortably across these images. This is a very small data set. We were able to extend it in a future version of this project. But in this initial project that I'm showing you now, it was only an image data set of about 50 images, and we got fantastic results. On top of that, there's a second part of it, which it was able to remove echoes delicately from inside the tissue, not just on the edge. The way we removed those as well was quite clever. We had to do something in order to remove those without leaving dark spaces, but that's not the focus of this talk right now. I'm just having a look at how we managed to identify those regions. The third step was then to identify the boundary at the bottom and then remove everything from below that. And so just applying this object segmentation to this image, the final result looks something like this, where we had nice dark space at the bottom. We didn't directly remove the echoes on the side. We actually muted them. We reduced the intensity down to about 10%. So in case there's something of interest there, at least some of those features are preserved, not entirely removed. And in a future version, we actually managed to enhance what happened inside the tissue as well. We didn't just leave dark lines in the tissue, but that is using some other technology and not object segmentation. So this is the beautiful final version of it. And the client was able to use this, and this provided the technician with significantly cleaner images to analyze. And this is just a great application we found of how to use AI in medical imaging to clean up the image and not just for diagnostic purposes. How do you guys get access to this? If you guys were interested in this kind of tool and you'd like to use it in any of your work, you guys are welcome to sign up. It's easy to sign up. You can sign up as a student. The simple philosophy of firststep.ai is not one of these where you have to pay to have access to all of the features. You get access to all of the features up front. You can design any project you want. All of the different models are at your disposal. It's free to design. Only when you want to deploy it to a production environment, only at that point do you pay. So if you're deploying this to a medical client yourself, at that point there'd be a paywall. But if you want to design it, run simulations, run images through it, all of that is free of charge from an academic perspective. To add to this, we've been working with the BICA conference as well to provide the best paper for the BICA 2022 conference. We'll get access to 6 months for a full professional license where you can deploy this to any final production system. So really looking forward to seeing who gets awarded the best paper and hopefully working with that person to build some really amazing models and get a chance to test out some of these new features. And so that's just the end of my presentation. Are there any questions? And thank you everyone for listening.
Sorry, thank you very much, Lynn, for your presentation. We have a question here in person.
Hi, Lynn.
Hi there.
In your version of the best, can you come back to the best image that you got?
Are you talking about the final image?
Not this one, and this one, the final process. Well, yeah, this one, the final result. Well, in this image, we still see some stripes there. What is the difficulty of trying to not having these stripes, or if these stripes are some kind of noise, or if they are a result of problems in the processing of suppressing the noise? What is the reason for these stripes being still there?
Are you talking about the stripes in the image here that are not necessarily horizontal? Are you talking about the ones that are curved?
Yeah, I'm talking about the horizontal stripes.
You're talking about the horizontal ones, the dark lines?
Yeah, the black ones.
Yes. So the black ones, in this case here, we used object segmentation as the first step to identify where those lines were. The final version we deployed on the clients actually took it a step further and said, how do we remove those lines from the tissue, which are right in the middle here, and not leaving these dark lines streaked through the image? And what we did was an interesting combination of interpolation from what the image, the pixel directly above it and the pixel directly below it would be, and we effectively faded it in order to take the average of what would be behind that stripe. I don't have one of those final images to show you, unfortunately, today, because this image just focuses on what we did with the object segmentation.
But don't you think that it would be possible some kind of interpolation and trying to fill up the black dots and try to give a more realistic final result?
Yes, that would definitely
suppressing the parts that were diagnosed as noise.
So blacking them out like we've done in this particular image, you're right, is not the best way of presenting this in the final state to the technician. We do need to figure out what is behind those echoes. In some cases, as you'll see a little bit further down, there's non-horizontal lines, which are like going in curves. These are actually part of the fibrous tissue inside the breast. So we had to be very careful not to remove those and only identify the horizontal lines, which were characteristic of the echo.
Okay, thank you.
Thank you very much for your question. It's a great question.
Does anyone else have a question? We still have 4 minutes left.
Well, maybe I can ask about the last part.
Yes, please go ahead, Alexei.
Lynn, what you offer for our prize winners, like what sort of the deployment would it be, and what would they be able to do that is not available to any participant that does not pay for a subscription to your services?
Absolutely. All right. So designing an AI model, any of the students can do free of charge. It is no cost to designing it, adding images, creating the best model that you can. If you want to take it out of the system and you want to put it, let's say, on a mobile app in order to be able to walk around and use this, we've just done this last week with a farmer. They wanted to take photos of their produce and analyze how many objects there were. It was counting fruit and fruit trees, and they wanted to have it handheld. They want to be able to walk around with the mobile app. And so we're able to build mobile apps like that from templates. It takes about 2 minutes to build an app using your model. So if you want to take it out and use it in a practical setting, I think mobile would probably be the easiest, whether it's detecting license plates in vehicles as they're driving past, or whether it's detecting fruit for farmers. The professional license will allow you that option to download it onto a mobile device and use it practically.
Mm-hmm. And that includes Android and iPhone, I guess, right? iOS.
At the moment, Android is supported. Yes, Android is the primary platform supported.
And iOS?
Not iOS at the moment, but that is coming soon.
I see. So again, which part of this work will be done by the student and which part by your company? I understand that the student designs the model. What does it mean? Just to write the algorithm, the code, or what is the requirement for this model so that you can deploy it?
Absolutely. In order to design a model, what it is you come up with an idea, say, I'd like to do object detection, object segmentation. You have a problem that you bring. If you have those images, especially if it's a visual one, if you have images, you'll upload those images, annotate those images, train a new model with a one-click button, and that will then have your model trained. The system takes care of all of the back-end choices and all of the fine-tuning that needs to happen. So we've had students come and within an hour or two have a model beautifully trained that does something for their particular problem.
Mm-hmm. And it can be used then on any iPhone, on any Android phone, or
with a professional license, any Android phone. Yes, your Android phone that you have in your pocket, you can deploy it on that and demo it.
Mm-hmm. Well, thank you. I guess we will learn more details in one-on-one conversation then. Thank you.
It's a real pleasure. You're welcome to reach out to me if you have any questions.
Pleasure meeting you.
Great. Thanks for the opportunity.
They have another question, but unfortunately we're a little short on time because if I recall right, Sophie Hendricks for the next presentation is here, but I'll make sure to let the audience know where to reach you with any questions. So Sophie Hendricks will present the roles of person-specific and person-independent behavioral adaptivity in affiliation and bonding. Sorry. Hello. Sophie,
yeah, hello.
welcome.
Thank you very much for the introduction, Felix.
And are you ready to share your screen, Sophie?
Yes. Can you all see my screen?
Yes, we can see pretty good. Thank you.
Okay, cool.
Please go ahead if you're ready. And you have 15 minutes and time for questions.
The Vrije Universiteit Amsterdam. And today I'm going to tell you something about the work of Jan Treur and myself regarding the roles of person-specific and person-independent behavioral adaptivity in affiliation and bonding. In our previous work, we have included several central mechanisms in human interaction, and these are the sensing and sensory representation of each other, mirroring the other's actions and preparation for own actions, internal simulation through prediction links, detection of interpersonal synchrony for different modalities such as movement, affect, and verbal interactions, and synchrony is defined as the attunement of actions from the same modality over time, and the expression and execution of own actions. So we have included indeed all these mechanisms in our agent models, and these mechanisms are adaptive. And that leads to behavior adaptivity in the interaction. And specifically, we are focused on short-term affiliation and long-term bonding in the human relationships, so the relationships that agents build with each other. However, an interesting issue that's often left unaddressed in the literature, but also left unaddressed in our previous agent models, is that which of these mechanisms are specific for the other person and which are other person independent. While building a relationship with a specific person, it may be believed that the adaptation taking place is
I'm really sorry, Sophie. Can you increase the volume a little bit, please?
Oh, yeah, sure.
Because we can hear you pretty well when you talk, but in the video it's a little difficult. Please, sorry.
Okay, shall I go back then in the presentation?
Just try again with the video if you want, or you can present it in person.
Okay. Theories such as attachment theory, it is claimed that adaptations acquired in one relationship also have their effects in other relationships. Therefore, it makes sense to assume that at least part of the considered behavior adaptivity is other person independence. But then the question remains, like, what types of learning for the behavior adaptivity can we use? In other words, which learning or adaptation principles can apply to which mechanisms, so to be translated. And indeed, both other person-independent adaptation and person-specific adaptation can be included herein. And also control of these types of adaptations, like the adaptive speed of adaptation, which is sometimes termed higher order adaptation, is required for these behavior adaptation principles. Luckily, we have useful contributions from neuroscience, because mechanisms in general involve connections between states and also excitabilities of states. And here we can differentiate between synaptic and non-synaptic forms of plasticity. And Hebbian learning is then a synaptic form of plasticity, and adaptive excitability thresholds a non-synaptic form of plasticity. And we then need metaplasticity to control them. As a method for our agent models to address this research aim and also all these neuroscience mechanisms, we have relied on the network-oriented modeling approach from Jan Treur. The basic characteristics of a temporal-causal network regard connectivity with connection weights, aggregation, so the impacts on a certain state are aggregated by some combination function Cy, and also the timing, so the speed factor eta y for all states y. And here you can see the canonical difference equation model in which all these things, so connectivity, aggregation, and timing are included. A network model is adaptive if some of the network structure characteristics changed over time. Like you have connectivity adaptation through changing connection weights, aggregation adaptation through changing combination functions or changing excitability thresholds, and also timing adaptation through changing speed factors. However, how can the model, a network model itself? By adding a self-model to it, a subnetwork with states representing network structure characteristics. We have the different possibilities, and we can create self-models for connectivity, a self-model for aggregation, or a self-model for timing. Like, for example, representing the network characteristics, connection weights, omega xy, through the self-model state wxy, a combination function parameter tau y, through a self-model state ty, and a speed factor eta y through a self-model state hy. And then the challenge, of course, remains like, how can we map a behavior to neuroscience to self-model states? So we have short-term affiliation that's based on non-synaptic plasticity of excitability thresholds. Therefore, we need the T states for excitability thresholds. We have long-term bonding that is formed by synaptic plasticity of connections within persons. And therefore, we use the W states for connection weights. And we have metaplasticity to control both of these types of plasticity in a context-sensitive manner. We have the H states for adaptation speed, and that's respectively the HW states for the W states, of course, and the HT states for the T states as self-model states. Here you can see it even more differentiated, our different types of adaptivity that we have built in our agent model. So at the first order level, we have the W states, and they are used for over time responding stronger to a specific person or agent over episodes. So it's other agent specific, and it's also adapted over episodes of interaction. We also have the T states to become over time more sensitive for a specific person within an episode. So they change within episodes. They adapt them instead of over episodes, as you can see over here. Then at the second order level, we also have a couple of remaining states. These are the W states, generation characteristics, the W states and the TW states. So, and they are used for over time to respond stronger to anyone. So it's other person independent. We have the T states generation characteristics, so WT and the TT states to become more sensitive for anyone over time. Then we also have the HW states and the HT states, as mentioned at the previous slide already shortly, and that's to adapt faster to anyone over time. And here you can see a base level of an agent A, as how it is designed within our agent network model. So we have sensing and representation states for different modalities of others, in this case for an agent B, C, and D. Then the M for movement, the B for effects, and the V for verbal actions. So sensing others, representing other states needed for that. Then we also have then the base level of a single agent, preparation states, and also execution states, and synchrony detection states. And the interpersonal synchrony detection happens by comparing the sensing states of the actions of another agent by the execution states of the agent itself over time. Then we go to the aggregation states at the second order level. Here you can see them displayed. So we have aggregated sensing, execution, and synchrony states, and also aggregated W states. And they are used for the speed adaptation, as you can see over here, that all these are indeed used over here. And then you will see over here, again, for the same single agent, the first order level, so the W and the T states, as mentioned before. Then we have the long-term adaptive mirroring, so the W states for the connections from the representation to the preparation states. We have also long-term adaptive representation states. These are the W sensing representation states. We have long-term adaptive execution states. We have the short-term adaptive representation states. So these are the T states with excitability thresholds for representation states of agent A, and also short-term adaptive execution T states. Then we have created an experimental setup to evaluate the behavior of our agent models. Then hereby we have used a number of expert scenarios in a group of 4 agents. So an agent A, as I've shown you. Then we have also agents B, C, and D. They have actually the same states, but they can have different state values. Then each agent randomly has then episodes of interaction with one of the 3 other agents. Then indeed have random selection of 2 agents for interaction episodes, random selection of the length of interaction episodes, and as well random selection of the length of a break between consecutive interaction episodes. And due to these episodes, they display both short-term and long-term behavioral adaptivity, and then other person-specific and other person-independent adaptivity over time. You will here see an overview of an example experimental setup. Here you can see our 4 agents A, B, C, D. Then 1, 2, 3, 4, 5, and it can continue after the 5, of course, are then episodes in which they can interact with each other, the randomly selected agents. So in the first episodes as agents B and D. And the episodes of interaction differ in their time lengths, and also the breaks between them differ in their lengths, as you can see over here. Then the experiments we are still conducting at the moment. So that's work that is in progress, and you will read in our paper then after this conference. But yeah, now I hope that I've given you a nice overview of our agent models. So as discussed before, we have a variety of mechanisms that play a role in the behavioral adaptivity emerging in human interaction. Our research aim was which of these mechanisms are specific for the other person and which are other person independent. And therefore we have designed a second order multi-adaptive agent model, including person-specific and person-independent plasticity. The metaplasticity was used to control these types of plasticity. Our agent model can serve as a basis to develop adaptive virtual agents that are able to affiliate and bond in a human-like manner. Thank you very much for your attention. And if you have any questions, please let me know. Thank you.
A więc postanowiłeś zacząć uczyć się polskiego, a powiedziałeś...
So are there any questions?
Yes, please, if anyone has any questions, raise your hands, either in person or through the online app. In the meanwhile, thank you so much for your presentation, Sophie. Very interesting.
You're welcome.
Seems like we have a question here. No, sorry. Doesn't seem like it. Well, in the meantime, I have a question, if nobody in the audience does. So, what kind of interaction did the agents have? Like, did you force them to have, I don't know, uncomfortable situations or positive situations, or?
So what we can actually do with the agent models is, so we have like states for them, and it's rather abstract at the moment with movement state for each agent, or verbal action state, or affective state. But we can then design scenarios around them. So for example, the movement can be seen as that they, for example, shake hands, whether or not they do that, or that one agent moves quickly and at a high activation level. So it's a very movable agent, while the other one is not. With the synchrony states, we then try to see whether or not they're actually at the same level of movement, or that the difference are rather small between them or not. So if they go with each other. So it's actually not that the specific movement is really displayed, but these are states that can be used then for movements that can be designed then in the situation that you want to use them. So it's actually a rather general model. And that also, I think, is a strength of the model, because you can then apply it to a variety of situations. So we often use it for therapy sessions, for scenarios used by that, but can also be used in different ones. I don't know, does that answer your question or?
Sorry, yeah, thank you very much, Sophie. If no one else has a question in the audience, we have 2 minutes and a half. I think we can close this block. Thank you very much for both presentators who were here, Sophie and Lynn. And thank you to everyone in the audience for being here. We will resume at 12 o'clock Guadalajara time. And thank you so much again for being here.
Thank you.
Okay.
Good day. I'm going to be the chairman of this blog. And we shall first to Vladimir. Is here Vladimir?
Yes. Yes, I am here.
Okay, you can share your screen?
Yes. My screen is.
You're gonna present us a model of how autonomous agent forming its own simple knowledge task.
It is visible, my screen?
No.
No. It's sorry. I will improve. Sorry. And now?
Yes. Yes,
yes.
Yeah, you have 15 minutes to present your work.
Okay.
Followed by 5 minutes to questions. You can begin.
Our work is a model of autonomous agent forming its own simple knowledge base. The authors of the work are Zarema Sokhova and I, Vladimir Redko. We are from Scientific Research Institute for System Analysis. Our approach. We believe that internal models of biological organisms use knowledge bases that characterize the features of external world and are used when interacting with the external world. We consider in this work a rather simple knowledge base of autonomous agents that generate and uses the cognitive map of the external world. Model description. The external world of an agent is a two-dimensional cellular world. In this world, the agent can eat and move. The agent at eating prefers certain cells. Being in such cells, the agent can successfully feed. The external world is rather small. The number of cells along one dimension is of the order of 10. The levels of food in the world is the following. We select several cells with highest level of food. These cells are excellent cells. The cells that are close to these excellent cells also have good nutritional properties. These cells are good cells, and other cells has not food, and these cells are bad cells. This picture illustrates our world. Example of our worlds. It is nutritional sports in two-dimensional world. Here are excellent cells, good cells, and bad cells. Dynamic of the agent resource. The agent resource, any agent has its own resource. When the agent eats in excellent cells, its resource increases on rather large value anytime steps. In a good cell, the resources increases, but something smaller cells. When the agent moves around the world, the resource is reduced by a certain amount. This amount is delta R. Agent actions and agent motivations. Agent can perform two types of action: to eat in the cells, which is in which it is located, and move and explore the external world. During the exploration of the world, agent can look new places where there is a lot of food. Agent has two corresponding motivations that determine its behavior: motivation to eat and motivation to explore the world. At any time moment, there is a leading motivation that determines agent actions. During the functioning of the agent, there is a switch between leading motivation. We believe that there is some inertia in switching motivation. There are two thresholds that characterize process of switching of motivations. Rather small threshold, a rather large threshold. This small threshold, large results. If during the process of nutrition the agent resource has exceeded large threshold, then the agent becomes actively motivated to exploratory behavior. If the agent resource becomes less than the small threshold, then the agent becomes actively motivated to eat. That is, leading motivation is to eat. Exploration or movement. Then at exploration, the agent begins move in arbitrary or 4 directions, and then moving, the agent does not change its directions until it reaches nutrient spot or it reaches a boundary of the world. The information about nutritional properties of cells through which agent passes past, and those cells of nutrition spots that are looked in new nutrition spots, the agent enter in its knowledge base. Results of simulation. The main parameters are the following. The world is rather small. The number of nutrient spots is equal to 5. The value of increased resource at eating in excellent cell is 1. The value of agent resource increase at eating in good cells is 1/2. The agent resource decrease when the agent pass one cell while moving around the world is delta R. The resource thresholds are small threshold and large thresholds. Results of simulation. The model was analyzed by means of computer simulation. The results of simulation are shown in the next slides. If after 100 time steps, the knowledge base is shown in this figure. The knowledge base after 1000 times steps is shown in this figure. In this figure is shown all nutrient spots are realized. Information about these spots is included into knowledge base. Dynamic of resource is shown at this figure. If a resource is small, then the agent become to it, and if a resource is large, the agent investigate the world. Coordinates of cells visited by the agent during 100 time steps and 2000 steps are shown in this figure. This figure shows that the old world is investigated. Dynamic of leading motivation is shown in this figure. It is shown that the main time the agent is investigating the world, and small time the agent investigate was eaten. We also analyzed the process of formation of knowledge base by the agent in more large world. The results of this analysis are described in the conference article. The conclusion. It is shown that in our model, the agent exhibits natural behavior. It feeds when the resource is small and analyzes the external world, then the resource is large enough. It is shown that with a small external world, the agent quickly forms a complete complete cognitive map of the environment in its memory. The dynamic of switching motivation that determines the agent behavior is demonstrated. This figure shows authors of the work. Here is Zarema Sokhova and I, Vladimir Redko. Thank you.
Okay, thanks. If someone have a question from the audience, please raise your hand. No questions? Okay, thanks, Vladimir, for your presentation.
Thank you. Thank you.
We will continue with the next presenter. They are Sufei Wu and Jan Treu is here.
Yes, hi. Hello, can you see me or hear me?
Yes.
Hi.
You can share your screen.
Okay. But Vladimir, please, can you stop sharing your screen?
Vladimir, your
and I can,
screen
yeah.
is...
Oh, my screen. Okay.
Yeah.
Yeah, stop it.
Thank
Okay.
you.
Okay.
All right, then I'll share my slides.
Okay, you have also 15 minutes and followed by 5 minutes for questions. Okay.
Thank you.
Begin.
Okay. So, hi everyone. My name is Yufei. I'm from the quantitative psychology group at KU Leuven, Belgium. So good afternoon or good evening wherever you are, but greetings from Belgium. And today I would be presenting my model of a highly sensitive person. This would be a integrative adaptive network model for the mechanism behind a highly sensitive person. And this project is a collaboration with Jan Troysch, the professor at Free University of Amsterdam. So I would like to thank you, Jan, for your support for this modeling process. All right, so let's start from the definition of a highly sensitive person, because it's apparently a folk concept, right? But if you try to search this term in psychological literature, what you would find is a term called sensory processing sensitivity, the SPS. So a highly sensitive person is someone who scores higher on the SPS scale, and which means they have higher sensitivity to environmental stimuli, and they have deeper information processing. They also have stronger emotional reactivity and stronger tendency of behavior inhibition. So these are the four characteristics for a highly sensitive person as a behavior level. And as you might notice that these four characteristics are interrelate with each other. And in the following model, I would try to demonstrate how they interrelate together. All right. So SPS is a relatively stable trait across one's lifespan. So a stable trait must have its own biological foundation. And the most well-studied foundation of SPS is serotonin, which is a neurotransmitter inhibitor that many of you might be familiar with. So what does serotonin do? It can decrease the dendritic spine density. If you can see the figure on the right, the dendrites, right? And it has some spines on it. And serotonin can also increase our inhibitory control. So the conclusion would be that a lack of serotonin will lead to a certain level of neuronal hyper-excitability. All right, I hope that more or less makes sense, because serotonin is an inhibitor, and lack of an inhibitor would lead to hyper-excitability. So let's take one step further, even, yeah. So the serotonin transportation protein gene here, it has two variants, the short one and the long one. The short one represents more efficiency, more effective serotonin transportation. So we have talking about the behavior level of a highly sensitive person, the neurobiological level, and even the genetic variance level. What I would like to do is merge these three levels of traits together. And how can I do this? All right, we do this as a adaptive network model. And here you can see its graphic representation. And the characteristic of the network model, Sophie actually has already mentioned it. So I will start from the biological line here. So let's start from the gene, this node, this state of gene, and a certain type of gene will lead to a certain level of serotonin. So this connection here is an indication of causality, and the arrow is the direction of the causality. And from the serotonin, we have the spine density. Here is a minus sign, indicates this is a negative influence. And all those previous states, they contribute to a certain neuronal hyperexcitability of a certain person. So this is the biological line. And let's move to the behavior line. Also in the pink panel, the base level. So on the behavior line, we have the first node, which is the word state, our external word. And the next is assess the sensory state, which basically means how much you do pay attention to the word around you. And the third node is the sensory representation state, which means the depth of processing. So the more deeper your information processing is, the more sensory representation you have. All right, so this sensory representation state contributes to the emotional reactivity state here. This is the third characteristic of a highly sensitive person. And stronger emotional reactivity leads to a stronger behavior inhibition tendency. And this state has an active impact on the preparation state of action and the executional state of action, which is the behavior inhibition itself. Yeah, this is execution state of action is behavior itself. All right, so this is the base level of my model. And now the question is, how can we combine the biological line and behavioral line together? So here it comes to the second, actually the first order of this model. Those states with capital T, TSS, TSRS, what are they? They are the threshold of sensory state and sensory representation state. And the neuronal hyperexcitability, they has a negative impact on the threshold, which basically means if one got higher neuronal hyperexcitability, the threshold of his or her sensory state will be lower. Then this person is more prone to be excited. All right, so we have this arrow to those two thresholds. And on the second level, we have another assumption, which is this capital H stands for the speed factor, how fast the threshold is changing. Our assumption is the sensory state itself influences the speed that the thresholds are changing. All right, so this graphic is basically all of our assumptions on the model. So I tried to run 2 simulations based on this model, and what I did is get all the parameters preset and only manipulate this connection. So it's from the gene to the level of serotonin. For a highly sensitive person, I assume that this person is lack of serotonin, right? And their gene type just indicates a lower transportation efficiency. So this connection weight, it's set to be 0.2. And for a less sensitive person, this connection weight, it's set to be 1. This is the only difference between a highly sensitive person case and a less sensitive person case. And let's see the difference from these 2 cases. Let's see what we got here. So let's focus on the X5, this NH neuronal hyperexcitability here, which is the green line. Oh, all right, we can see that for a highly sensitive person case is almost reach 1. And for a less sensitive person case, is actually below 0.2. So the manipulation is successful, right? And let's move to the characteristics, the behavior level of a highly sensitive person, which is they are more sensitive to environment. And this should be represented by the SS. That's the dark red line is still very high, right? It's around 0.9. And for the less sensitive person case is around 0.7. And for the depth of processing, we can see here, this is a sensory representation state. So it's still high, above 0.8. And for the less sensitive person case, it's much lower. You can see it here. And then we have emotional reactivity, the orange line here. It's higher than the less sensitive person case. And we also have the behavior level, the behavior inhibition, this light blue line. This also fits our hypothesis. So this is basically my model and simulations of a highly sensitive person. And my conclusion on that is, I think this is just a promising model, and more empirical data can be collected to validate this model. And also more scenarios can be explored based on this. Because if you see, if you pay attention to this, this is quite a isolated example, because the person is not interacting with anybody, and it does not have a interaction with the environment, right? It only has input from word state 1 at the beginning. So it's just worth it to try more scenarios. For example, how a highly sensitive person interact with a less sensitive person. How do people with a different level of sensitivity interact with each other? That's those are all very interesting questions, I would say. Yeah. So thank you for your listening and attention. This is my email. If you had any further question or something you want to discuss with me, you can just email me. All right. Thank you.
Thanks. If someone of the audience have a question, please raise your hand. Okay, no questions. Thanks for your presentation. This concludes the presentation of this block. Thanks to all the presenters and to all the members of the audience. The next activity we have scheduled is a coffee break of 20 minutes, after which the program will continue as scheduled. Thanks.
Well, good afternoon. We continue with our program. Now, I am the pleasure to present Emanuel Ortiz Lopez. Emanuel Ortiz Lopez obtained his bachelor degree in Communication and Electronic Engineering in 2009, and his master degree in Electric Engineering in 2011. Currently, he is a PhD candidate at the University of Guanajuato, and he is working as engineer, as a research engineer in Continental. And today he is going to present us the work they are doing as application of the artificial intelligence in Intel. And that is a very, very important work because as you know, Continental is one of the main companies working in the automobile industry. So please, when you want, you can start. You have more or less 45 minutes for your presentation. After that, people who surely will be interested in your work may ask you some question. Go ahead, Emmanuel.
Thank you. Hi, everyone. Greeting. I am Emanuel Ortiz Lopez, as I mentioned, currently as an engineer in Continental R&D Mexico. I'm part of the Autonomous Mobility group in the line on a team called Innovation Line Driverless. Today, I will speak with all of you about the one topic that is very important for the company. I think for any area related with AI, it's called interpretability, in the sense of how they have an understanding how the models and how it works and validate the performance of how they should work. A little bit of notes, basically, how to mention in Continental, as just short to say, we are a company that do more than tires because we are focused more in mobility, and in the last decade, basically, we are providing a ton of technology. Currently in Mexico, at least have at least 20,000 employees. Is the biggest workers force outside of Germany for this company. So actually, the bigger than now, we have 2 R&D centers. One is in Guadalajara, and the other one is in Querétaro, where I am currently working. So we are more focused on these areas of safe mobility, smart mobility, autonomous driving, architecture networking. Is beyond the this not only on the car, but also the infrastructure around the mobility. And we're currently working. We are working in challenging status quo of mobility, and we believe in thinking different. And actually, we make a huge bet to how to do research and development and improvement technology from Mexico to the world. Okay, we are working in that sense. So let me start a little bit at this point. What I mean, because in introduction of this conference, I will speak of artificial intelligence or AI, but I have to I think I should be more specific on what I mean with AI. What is AI? What the shorter answer is a mathematical method for prediction. And specific where I'm more focused on what's called narrow AI. So it's basically it solves highly focused set of tasks. And what I mean with that is the task even can be automated in a way, but the machine can be perform better as in a way that even a human can do, but it's all based on human perspective. No. Currently, for example, we have examples of voice assistants, of the textures, chess, go play in algorithms, all of that. So I'm focusing that focus on this application of interpretability in this area of narrow AI. It is this search or have the increased interest in this topic come from science students and at the boom of deep learning. What is deep learning? And summary, just a simple chain of continuous geometric transformations, which projects one space vector into another. These series transformations or projections assumes the existence of learnable parameters to transform the input X into the desired output Y. This type of methods or this type of networks have a big boom since 2012 when ImageNet, AlexNet outperformed the top 5 error. So actually, when I mentioned these continuous transformation and geometric transformations, is when we can see that we know that the deep learning provides solutions, but not all the time it's clear in which way or fashion we get the results of what is provided at that point. So interpretability, as this cartoon from the New Yorker explains, is how to get an idea, for example, in autonomous driving, whether you can pull it, or understanding what is the decisions or what make the decision of the AI algorithm or model to how did they reach that solutions. And the first approach that we get when is interpretability is basically interpretability helps to fulfill something that they call it the under or super specification problem. What I mean with that? Well, when we, apart from AI, pretty much we get a black box, and we assume that we assume a solution, but we don't have clear, for example, what is important for the model, or what is should be relevant, or no, or what should not be relevant, for example, or what must be avoided, and a problem to be solved. So when I work in interpretability, the first point of interpretability, we feel that under specification problem, or what we mean on AI applications. We can ask, for example, one example, an example under specification will be, for example, what is safety? Safety for who? For what? When is a safety? When that is the simple question that not only involves the training of the model, observation of the model, but also how to annotate the model and how this. Because if we understand all of that, we can now not only so to say debugging, but also found liability and failure test and what is the model doing versus what it's doing. All of that interpretivity is required or something that should be needed, and the question is yes and no. And sorry, maybe was here, but the reason why is yes and no is if this is a sensitive domain, for example, credit scoring, finance, healthcare, and self-driving cars, for example, yes, because you are liable for what the AI model does, what the decisions they make, what the solving the problem was. There's a liability in that problem, but you don't need, for example, interpretability if the model, for example, if the application of the model doesn't have significant consequences. If something goes wrong, it doesn't happen nothing. The other will be that the problem is well studied. For example, you have another solution that you exactly know what's happening, how to solve it. So not all the time. So I think we have to spell the criteria. Also becomes the yes and no, to be more clear what the yes and no, for example, is not always the test sets accuracy testing guarantees that the model have a desired behavior or resolved by the desired properties and problems. So I can be a little bit more detailed than that. for example, interpretability, when I was speaking about interpretability, I didn't speak about translation. And I mean with that is, I don't need, for example, translate every filter, every weight from model to numerical representation, because at the end of the day, numerical value doesn't have, how to say, a translation. The example that I put here, for example, is in Japanese, you have the word komerebi, that means sun shall fit into leaves, but that same word doesn't have such equivalent as a word, as a one single description in English. But there are another way to put it. Every translation is a translation. Sorry, is a traitor. Every translator is a traitor, so to say. So what we need to understand in interpretability is understand that it's a problem to see if the model have the same properties that are aligning with the goal of the model and the downstream task. So we can focus on that problem. A problem. Basically, the goal of interpretability is that our values of what the people designing the model, implementing the model, are aligning with the solution. And also that the model reflects at least some kind of intuition, learning process, or the expert knowledge is desirable of the people that planted that model. An example I can mention is, for example, we can see the image I'm sharing, and I see the traffic light and two cars, for example. One example is if you run, for example, a traffic light detection, and you can see, for example, so some models will struggle with that because the models will see, for example, that light looks yellow. And actually, if you were the labeling team that will label that image to use it for the training, probably you will tackle that as a yellow, because indeed the light looks yellow. The only reason we know that traffic light is red is because we know how we have intrinsic knowledge that the position of in that light should be a red, not a yellow one. So when we plant a model that can solve that task, maybe we not only focus on the color, but also focus in the position of the light. So it's something very, it is important that the model should be aligning what we already know that it can be important to solve a problem. It doesn't matter if it does. Okay. Interpretability also have some criteria. The criteria for interpretability is that depends on interpretation points or a downstream task on a downstream task. And what I mean with downstream task is I mean that is the criteria is depends on who consume or will consume the product of the interpretability, the squaring explanations. And the people who will consume such explanations depends on the level of the information that is needed. For example, I put an example here from one user that you do during a service, see that it's informing that the automatic neglect require additional check, for example, but the agent of such a technician that is the agent, for example, that received the car, for example, the information that they need to know, for example, for the technician is that the light intensity sensor is having issues, for example, and the explanation, for example, the technician needs for fix that issue is that the ACU of the car needs an update or an updated firmware of the version. So everyone have the same, for example, same issue, but everyone needs different information, depends on what level of user you are on that set. So it's a way to put it. But also, I had to meet the biggest criteria for interpretability is that every explanation should be relevant to humans. That to say this, if information does have a mathematically solved, or for the other computer doesn't make sense for human, because we have different aspects of that. One of the biggest also challenges of interpretability is that interpretability is not the same thing as accountability, causability, fairness, and trust. But this is a way to reach that the concepts. That means some problems can be solved through interpretability to achieve accountability or causality, but other way sometimes you don't need that interpretability to achieve that such a thing. One example of that, for example, is in 2018, Reuters report this issue when where basically as a company have a machine learning model that reviews curriculums, CVs, and what this model was doing was pretty much was not taking as a candidate any woman to apply for a technical role. And the issue with that, honestly, doesn't need interpretability, because if you take a look on the expression, a good expression of the data, you can see that the data that they use, for example, is historic data of their hiring processes. When they reflect, for example, that at least in technical roles, the woman is still a minority in much of the technical roles. So they they leave, for example, these parameters of the gender in the condition of the model. So the model have assigned a very low probability that a female will be a good candidate for engineering. But if you see this one, you don't need interpretability to find this unfairness. But nevertheless, it's possible to use an interpretability to achieve something results of planted in that fashion. Okay. As I mentioned previously, the biggest or the product of interpretability in particular case is explanations. And explanations should be accurate, so like an accurate reflection of the model, and have to be meaningful to humans. The explanations can be split in two categories. Basically, there's the local ones that basically explain a single point the best as possible. I mean, which point, for example, lead why a model take this point and explain the result of that point the best as possible. Or you have the global ones explanations that provide a general description of the behavior of the model. And two subcategories of that will be model specific. I mean, models that are explanations that are specific to a certain model. I mean, you have pretty much an insight of the model, and model agnostics. Pretty much you deal with them with the model as a black box. Okay, so you have this paradigm, but the same again, the product of interpretability is called explanations. We have different ways to get interpretability. For example, we have interpretability before any building any model, and this interpretability comes from data analysis, visualization of data, statistics, anything that helps you to understand what our data data performs, where it comes from, how can be used, anything that gives you a better insight of how our data is used and around. So this understanding is very critical, because we assume always that we only need more data to have a better model. But at the end of the day, data is made by humans. Any data that comes from humans is dirty. So we need to be very, very thoughtful about have a very good look on our data. Later on, we have something is called interpretability by design. I mean, we are now building a model. So we start building a model so we can get interpretability into fashion the process of building a model. One is get models that are designed to be interpretable. In this case, for example, this is a neural backpropagation trees. Basically, it is the backbone of a deep neural network, and it's replacing some part of that for a decision tree. And this way, for example, it is expected that we understand how every inference, for example, every decision is made. The issue with that is depending on the complexity of the decisions, of the number of layers, of the models, eventually, even in a decision tree, stop to be interpretable because it's very huge and certain limits. So follow how, why in decisions becomes very difficult. And listen, from the human perspective, because the humans need to consume this information. Okay, this is one way. It's interpreted by design. Another way you have interpreted by design. For example, we see in the previous slide about explanations. For example, you can now do something that's called knowledge distillation. Knowledge distillation, is get a huge model, transfer, train it well, performing well. When analysis is performing well, you distill that knowledge to a smaller, translate, interpretable model, so you can get that one. But nevertheless, also depends on the complexity of the task, the complexity of the data is managed, of the sort of levels, is not directly applicable. Not always interpretable. Okay. Other approaches, and this is phase of building a model, for example, is getting inside of what the model is learning or doing, for example, or struggling. One example of this I like very much is something called Bayes gradients. Bayes gradients is a valuable, expensive proxy metric for detecting outliers in data distribution. That's a meaningful way to rank the data by difficulty and show how manageable a subset of data is, or how much, or how challenging is to manage this data set or manage data to managed by the model. So we can now did, for example, the process of training. For example, we have an example here, for example, a model that have a lowest Bayes gradients, for example, to classify horses. When the horses is fully static, complete, but highest score in Bayes gradient when the image, for example, as a close-up of the horse or only one part of the horse. That meaning, for example, that you have a sort of lack of distribution, for example, in your data about the presentation of the horse in your data. So you need to move a little bit back and analyze your data and add more scenes or more description of the horse, because you have your model is not high weight performance when they are close-ups of the horses. For example, but this can be doing in the process of training. It's actually one of the best approaches I found out about this kind of in process building a model. Well, what happens if we receive a model? I mean, we don't be involved in the part of the creation of the model, so we can start after the building models. Very much leading as a little black box. The first approach we start is the ablation test. The ablation test basically is consider removing features of the input of the model to see the impact on the model. These methods are very much focused on local explanations. Here is the disadvantage of local explanations. Local explanations can be contradictory, and when I mean contradictory is we can take one point of this and explain it the best as we can for and one side of the, for example, and of the classifier, and explain the next month the other side of the, for example, I put here such a description, for example, explain another point of the to explain another model, another point for the model, and we can get an explanation that will be contradictory for the first one. And so to say, for example, an example I like it, for example, this is, for example, using in finance. In finance, for example, if I can submit a credit, such a credit will be approved, for example, in 1 point, for example, and tell me that my my credit is approved because I am Mexican. But if I take a look at another point, age or whatever mean, more another point to explain, for example, this such a point can explain that I wasn't approved, the credit wasn't approved for me because I am Mexican. So this has happened. Doesn't mean that it's not important, but when we take look at explanations, we focus on what points are critical for us to explain the explanation. So there's a bunch of methods that deal with this approach of feature removal. So I think such a thing, for example, involves shape values, so like that. Next on, move on to another approach after building a model. We can do investigation of the hidden layers. This approach, for example, is not a black box, but we can detect the model, for example, is see internal activations of the filters, of how the filters are performant when expecting an input. For example, one example of this approach is called the TCAP score. The TCAP score, for example, tells you that you should provide a concept that describes what is unique or relevant for your point of view for the class to be important. In this case, for example, it's proposed that the stripes are the very highest or higher feature that will provide the description of a zebra. So we need to focus on that. Sorry, I said. So we take an example. What TCAP does is take a zebra, we apply feed the model with the image of the zebra and recollect the activations or the information of the activations layers. We provide also images, for example, with the stripes and see the actual activation of the models or the distribution of the layers. And we provide random concepts to see and also get the activation of such images. Later on is building pretty much a linear classifier, and the magnitude of the orthogonal of this line, a linear classifier, is the higher the score of the score of such a TCAP method. The higher the score is, the higher the importance of that feature is which this feature is intrinsic to the class. How the score is, how important that the object, that feature is to get the right classification. The issue with that approach, because have an issue and all this advantage, is a powerful one, but have the biggest advantage that every feature will have a unique intrinsic description for every class that you want to get. One challenge I can put in that kind of solution, for example, is how you can get a visual concept, a description feature that is different, that can make a difference between a dog and a cat. You don't have that value. Such a solution maybe is hard, so we can move for that. There are more methods. I only mentioned the biggest relevant, at least that will describe pretty much the template, the thread is inside of this approach. But for example, how we can evaluate or we can choose with method repeatability we can use. Well, first of all, the biggest challenge, as I mentioned before, of repeatability is fulfill this on the specification problem. So the first step is formally describe the cyber properties of what you want the model does and doesn't do. What I mean with that, you should be what things the model should do and what things the model shouldn't do. And this is important because we can, after describe the qualitative features, we can apply quantitative features to measure such a cyber properties. We can define a formulated grant or experiment that can serve as a grant truth, and do experiments and choose on the methods that maybe can help us to formulate such experiments. Okay, Later on, we have, for example, one idea how to evaluate such interpretability methods, because no only for us, we can make ideas, because also we want that the interpretive methods are better than educated guess, are better than a random guess. So we can, how do we make sure that the interpretive methods are working? One of the approaches, for example, a good example of a correct implementation of this is the ROAR work. Pretty much what this model does is, this model identifies which vectors are important for the classification. This one are removed, and later on remove it, and also the model later on train it with such data, such data with the removed features, and if the performance, if the model start performing poorly, the comparison of the previous one, and have decided to have the same data but not the same features anymore, you can say that actually your explanation is correct, and you have the right features why the model is detecting one, and you have one explanation of that. A quantitative aspect, because also you can measure how important such features are for the model. Another approach, for example, that I personally use this one in my work is called the elation game. The elation game pretty much is similar to the other one. Is you start deleting, for example, what the model will provide you as an explanation to which is important, and measure is if it start deleting until the model doesn't classify or detect that topic anymore. If the area under the curve or the feature removed is very, for example, very low, you can see that you have a good explanation. An example more detailed for them, this is an explanation. This explanation, for example, comes from a method called disrise. The method much is this addition test, remove features on the image, and then an object detector model. And in this case, for example, this explanation for the person and the image. You can see that, for example, the model is telling you, or the explanation is telling you, sorry, that the head, the arms, and the legs, for example, are important features for the model to detect a person. Later on, you can see we start removing the features for the more important to the lower importance, and you can see that if we, as soon as we delete such features of the head of the legs, the class person or this person in particular is lost. You don't have, so we have that feature is that features are very relevant for the model, and actually in this particular case, also as a sanity check, we take a look at the features that are also highlighted are intrinsic or related to the class, because sometimes then you will have, for example, detections for a class, but we'll use, for example, some background, some issues, something that is not intrinsic related to the object of interest. Here also a warning, because a lot of methods that you will find, at least for image classification, are related with heat maps. And I worked on 2018 for Adebayo. It shows you that if you are based, for example, in it's called a method that's called GradCam. It's very famous. Pretty much GradCam, if you use a network and you randomize the network and you apply an image, you have the same explanations as the model that is well trained, no version of random one. So you are your heat map is no better than edge detector. So you should be, for example, apply techniques such as elation test, such as ROAR, to make sure that the model is not your explanation, for example, is not just is not forcing a cognitive bias. What I mean with cognitive bias is, for example, what GradCam does is that because you have these areas of interest that is maybe focus in the area where you are expecting an output, you are telling that the output is expecting that the output is confirms your expectations. That is cognitive bias. That's something that we should avoid. A little bit of one explanation is on interpretability is a branch of what's called explainable AI. And currently, there are approaches to explainable AI in the industry. For example, a lot of them are focused not in the end users. That means that explanation doesn't come to the consumer of the product, but right now we use it, for example, to machine learning engineers, pretty much in a quality assurance way. That we want to debug and also have a quality assurance that the product or solutions doesn't have any issues. For example, in lots in finance, for example, you want to see the sense of completeness. I mean, completeness is that your model is solved by the right solution of what the grade should be provide. So we have this. It's a work. It's actually the paper is called that machine learning and deployment. Actually, I enjoy it. I recommend it. But at the end of the day, also these practices and the industry also comes today. These explanations are consumed by engineers, but also helps other teams, for example, management, stakeholders, to get transparency of why you are working on that topic and the solutions I provide. Okay, now we have our challenges. How interpretability. One of the biggest challenges is the state of the art of the interpretability is very much focused on two areas. One is natural language processing, and the other one is image classification. When you come from, when you move, for example, but both of them are working in linear architectures, such as, for example, BGD16. But when you move, for example, on another kind of architectures, for example, number detectors such as SSD or YOLO or other approaches, you have issues because the model is not linear, have multiple solutions. You have a multiple header. You can get the explanation, for example, in case of the detectors, for example, of a local anchor box, but doesn't mean the expansion is for all the anchor boxes of the are there. So there's a challenge in how to work interpretability in models that are more complex and not linear as a BGD. And that is for the moment. Thank you for your attention. If you want this in Continental, please visit our site. Thank you for attention.
Well, and thank you, Emmanuel, for your talk. And someone has some question for Emmanuel? Yes. Okay. Here in the audience, we have one question.
Hi. This idea of interpretation or interpretability, in some sense, is connected to a kind of subjectivity, in the sense that different people might interpret things in a different way. When we talk about machines making interpretation, how can we expect to find or to see this subjectivity materializing? I mean, there might be different machines making different interpretations, or we must converge to a single kind of interpretation. How do you see that?
Well, that's an interesting question. One of the biggest revelations I have working on this topic is the subjectivity comes from what is the goal of the model. And I mean, when the idea is attractive, that you have a single solution that you feed a model that have an object evaluation or description of the model, the explanation, for example. But sometimes what we are omitting is that even the user of such a model, for example, depends on the task. So the data or the model or the thing. So it's more related on focus what is the baseline of expectations on one task. Other than that, you can get interpretability based on the expectation of that task, not based on general one. And I don't know if that helps you. For example, one example I can say with that, for example, is very important. For example, in set is the this is the latest. I like it a lot. Let me move a little bit. This one. Depends on the level user. You have one criteria, but the same criteria of the repeatability, how make it hard is the first one. The user that we need for the explanation is important. So I get a machine that provide you an explanation. Okay, the product of the explanation is only a focus on one person that need to consume that sort of information. The reason that this information will be relevant for you is also set by you, but it's important for you that the model does or doesn't do, so it can be reported to you. So it's a working description of what is expected from your model, and what at least is not what expected. What is at least what expected as a good behavior, because sometimes we don't have all the solutions. For example, what explanations to resolve, but we want to have, for example, one that comes to my mind. For example, the use of the credit scores. Credit scores, for example, in the US is a big deal because all the information is based on in geographical information, and geographical information have a huge background, for example, of unfairness and racial bias, stuff like that. And when you talk, for example, this data and took it as it is, your model only will be increased that bias on that description on application of credit scores, stuff like that. And one thing that you can do for a model to avoid such a thing is that you are at the beginning of the creation of the model or the expression that you want to test or beyond test set accuracy is, okay, how well our model should be avoid this racial bias, for example. There's one way to see.
Okay. Someone else has a question for Emmanuel? Okay, if there is no more question, thank you, Emmanuel, for your talk. And we are going to continue with our program. Thank you, Emmanuel, once again.
Thank you.
¿Tú eres el chair? Sí. Sí, déjala ahí, porque es el speech. Sí, sure. Sí, faltan 10 minutitos.
We're going to start the next presentation at 2 o'clock, 14 hours. So we have a 10-minute break for you to go for a coffee or something. Or to eat something. Thank you.
Sí, adelante, Dina.
Hi, we're gonna start with our next session. The first one is gonna be Rafael Mercado. It's gonna present us his work. He's gonna sharing the screen now, and I'll mute this. Do you see the screen, the presentation?
I see.
Okay, I'll begin now. Good day, everyone. I'm Rafael Mercado, and I will be presenting paper number 64, Modeling of a Cognitive Hybrid Architecture for the Hydrothermal Regulation of a Room Manipulated by an Agent. The authors are myself and Drs. Vianney Munoz and Marco Ramos. We will begin by establishing the context of this research, which is hydrothermal control. That's the control of an environment's temperature and humidity. And as we can see with current events, optimization is growing in importance due to, first, the trouble with fuel acquisition, as well as the different societies' attempts at moving into renewable energies. Our approach attempts to implement a cognitive theory to specifically this task. Regarding current approaches to the task of hydrothermal control, this is an active field of research that aims to generate a room environment habitable and comfortable for residents with minimal energy expenditure. Examples of approaches are control strategies to actively change a room's hydrothermal state. Think of an HVAC unit or humidifiers and dehumidifiers, and that's what we'll be dealing with for this paper. Other approaches include scale management, which is to manage people themselves and spread them out across time so that their body temperature doesn't affect the room or bunch them up together, so it does. And finally, changes to standards and guidelines. This one focuses on changing the guidelines for building for new buildings so that their design is friendlier to the task of hydrothermal control. So we will begin by our interest in cognitive theory and cognitive architectures for this task. Since cognitive architectures, biological inspired, helps us to understand our function as living and thinking beings, they can also be applied to extract and model behaviors for specific tasks. And this is what we will be trying to do for this presentation. We made a cursory search for the cognitive architectures, the ones we list below, and the small facts about them, small characteristics of each one of these that we found interesting for our task. We begin with ACTAR. From this, we identify distributed modules that interact through buffers. From SOAR, long-term memory is represented as productions. From LIDA, global workspace theory, and attention codelets and how they override parts of some of the modules to implement their needs. And quite a little, since they handle motivation as a set of internal and external influences. We take these little facts about each one of them and use them for our task. And finally, this one's not a cognitive architecture, but for the sake of space, I place it here. And it's PRIMS, which is a theory of cognition, where cognitive tasks are divided as primitive information processing elements. Our objective with this study is first to identify cognitive theory for the task of hydrothermal control, implement this theory in an agent, and identify its viability to the task. For this study, we proposed the following case study. A room's temperature is susceptible to environmental pressure. The room houses an agent who constantly queries the room's hydrothermal state and can influence the room's hydrothermal state, can actively influence it. This agent has a goal state for the room, and we begin with each one of these elements. Initially, for the environment and its effects, we used data gathered from a weather station located in Toluca, Mexico. We took the average temperature for and humidity for the month of February, and that's figure 1, the one you can see to the right. The red line, the red full line is the temperature, and the dotted line is the humidity. This will be the pressure exerted by the environment on the room we will be modeling. For the sake of the future slides, we will be seeing these variables to make it easier to understand. For the room, we have the R variables, T and H. T means temperature and H humidity. And these ones are the room's temperature and humidity. For the agent, we have G and A. G is the agent's goals, and A is the agent's actions. Finally, for the environment, E is the environmental pressure. I think I will talk about this later. So basically, the agent's goals we gathered from information both from the World Health Organization regarding which ranges of temperatures are important for or best for human beings. The other ones are specific to the room we are modeling, the agent sections, and the environment we just talked about. Now, moving on to the room's model. We modeled it as a closed 2x2x2 space, enclosed by walls of 0.2 meters of thickness of variated concrete blocks. And for the simulation, we used a time step of 10 minutes per tick. With all this information, we made the calculations and ended up with the equation you can see below for the change in temperature in the room, which handles the room's temperature and the current environmental pressure, as well as the agent's actions. For humidity, we used the bit for saturation humidity, which means how much water vapor can be contained by the air in a given space. We also constrain humidity since it's a percentage from 0 to 100%, and 100% meaning the saturation humidity. Finally, we constraining it between those two values, we simply add the agent's actions. The agent's actions are 11 levels of action for temperature and 7 levels of action for humidity. For brevity's sake, I will only say that these values are based on commercial models you find on any market for HVAC units or humidifiers or dehumidifiers. And now we move on to our proposal for the agent's interaction with the room. First, every time step, the environment forces some pressure on the room, changing its temperature. In that same time step, the agent queries the room's hydrothermal state and sends that input to the attention module we will be talking about later, which defines whether or not to engage, rather to engage or disengage with each of the elements of temperature or humidity. As a consensus that we will talk about later, this consensus reaches procedural memory that we define as a second module for our agent, which generates a plan to be followed by the agent regarding the levels of action we saw a couple slides back, or the previous slide. This action, in turn, affects the room's hydrothermal state, and we can move on to the next time step 10 minutes later. Now, for our attention model, we used as a main reference the one you can see in the top from SOS. Regarding uses for visual attention, we took the elements that we could include into our current task, which is a subset of the ones he proposed. Now, they define multiple mechanisms for selection, suppression, and restriction in their modeling for attention. We take a subset of them and classify them as the 4 tasks you can see on the image below, which is to engage attention, disengage attention, handle external or internal factors, and select target of attention. The attention module receives the hydrothermal state of the room as input, knows the agent's goals, and retains the previous temperature and humidity of the room, as well as what happened in the previous time step, which is whether it engaged with temperature, humidity, none, or both. This module works as a consensus of the mechanisms regarding temperature and humidity, as we can see in this slide. For the consensus, each of the mechanisms has a vote, which is to engage or disengage attention on the target, according to the lists below. And the sums of votes for engaging or disengaging becomes the consensus and updates the variable of its memory. With this consensus, we then feed the procedural memory module, which we modeled based on a formal grammar based on L systems, which represents the agent's procedural memory. This grammar produces plans to change the actions of the agent on the room and receives the input, which is the hydrothermal state of the room and the agent's goals, as 2 parameters, which are the distances between our current temperature and the agent's goal temperature, and likewise for humidity. How our proposal works is through precisely a grammar based on those systems. This one consists of a tuple of 4 elements. The first one being the alphabet containing terminals and non-terminals. For ease of readability, the terminals are uppercase and the terminals are lowercase and the non-terminals uppercase. It also has a set of production rules representing procedural memory with the form you can see right below. An element non-terminal being B produces an array of elements, terminal or non-terminal or even epsilon, likewise in B, given 2 Boolean functions. These functions are dependent on the values of the parameters, which are elements sigma of our grammar. And finally, we have an initial non-terminal to begin the whole process. Now, for how this grammar flows, we took a bit of inspiration from how PRIMS handles cognitive tasks, which is to reduce them to primitive elements. Rather than reducing them to primitive elements, we focused each one of our production rules, given their non-terminals, for each one of the tasks. For example, production rules that handle non-terminal T activate when humidity is not being engaged, so they handle only matters of temperature, likewise for A and B. And the contrary happens with H, C, and D. They handle humidity. Now for this module's output, we have ultimately a word composed of terminals, which are A, B, C, and D. The number of appearances of each one of these dictates which level of action the agent will have. A and B dictate an increase/decrease of temperature. Likewise, C and D for humidity. In this way, we identify which level of action from the levels we explained earlier the agent will take in the given time step. Now for the results of the simulation. To the left, figure 4, you can see, first of all, our model of the room. Since our time step is of 10 minutes, it's easier to understand how it works. Basically, the room is fully dependent on the environmental pressure, and as the temperature of the environment reduces, so does the rooms. Likewise, when it increases. To the right on figure 5, we can see this same model, except with the agent's involvement. We see likewise the red line is the temperature of the room, the green dotted line is the environmental pressure, and the blue dotted line is the humidity of the room. We can see from the first step of the simulation, the agent overshoots the activation of its actions. This happens because it has no previous recollection of anything that has been happening, so it simply handles the distance. However, once this overshoot happens, it brings it back to its right. The shaded area is precisely the ranges that we talked about, the agent's goals. So the agent, once it overshoots, brings it back down and tries to maintain it within its goal area. Now for humidity, as I probably didn't say this before, however, humidity in an environment is highly dependent on its temperature. As the temperature increases, there is more capacity for water vapor in the environment. As it decreases, so does the capacity. Thus, whenever big changes in temperature happen, those big changes are also reflected on the humidity. And that's exactly what we can see. Sometimes it shoots up or down. However, it does attempt to maintain it within its goal range. Now, moving on to discussions. Yes, we see that further refinement of actions when the agent is within its goal range can increase the agent's effectiveness. This we can see from, let's say, precisely from the image. Sometimes it just shoots away from its goal because it doesn't really have much control when it's within its goals. Now, also reducing the time step will help reduce the magnitude of the jumps in temperature. Since our model handles the temperature change in intervals of 10 minutes, the first action of the agent has 10 minutes of action on the entire room. If we reduce the time of action, the agent will have more responsiveness to changes. And improvement may be achievable following the Prim's theory's approach to skill transfer. This again, since our first implementation of ideas from Prim's allowed us to make the grammar model, perhaps an expansion of them will help us further. And finally, conclusions. This paper presented a case study to implement elements of cognitive theory to hydrothermal control. The attention model addresses the room's temperature and humidity according to its needs, previous actions, and knowledge. And the procedural memory allows the agents to decide its actions to the environment and their magnitude. Finally, these are the references we used for each of the models and tasks we defined. Now, this is the end of the presentation. Thank you for your attention. If there are any questions, I will be pleased to answer them.
Any questions, please? Here's a question.
Let me try to explain you my question. When we talk about a cognitive system and we think about a cognitive system to solve a problem, usually we think that there might be multiple goals, different sets of goals, and then we use a cognitive system because exactly there might be many different goals, and then we need to first get the goal, and then you go to pursue the goal. But when we are having something like a control system where you have just one single goal and the system performs some kind of automatic pursuing this goal, I was just wondering what is the benefit of using cognitive theory for solving a problem that you can solve without a cognitive system, because it can just employ a rule-based control, what actually appears to be what you have done, because you're doing a rule-based control system for controlling this system. So I'd like to know what is the gain of appealing to a cognitive theory for a problem that has just one single goal.
Yes, that's exactly what I think about this. The reason I decided to start implementing this, since, I mean, this is not an excuse, but I am dealing with different, what would you call it, disciplines. So this is one of my first forays into cognitive theory or cognitive architectures. So that I simply can't apply. What I was thinking about is that if we have, or at least I have, a first step in the subject, now that I know how different elements, different modules, different parts of cognitive theory interact, I can expand on them and I can make it more general, so to speak, so that I can handle the tests. But certainly this is mostly control.
Any other questions in the Zoom room? Is there any other question? Question? Yes. There's another question. Okay. I'm not sure what I am going to say, but have you heard about the Internet of the Things?
I have.
Yes? Okay. So imagine that you have cognitive architecture controlling an IoT environment. So what kind of control do you need for this problem, for IoT? Do you think it is possible to use a cognitive architecture to control all the needs or problems that arise in an IoT environment? Or no? Or is a huge solution for a small problem?
Well,
sorry.
Well, that's also part of what I started thinking about cognitive theory. Certainly, I've been to some of these talks, and that cognitive architectures are certainly a big element, are capable of many tests, many general tests. But if we wish to implement them to simpler tasks, in the same way that I presented here, at least what I think how it would work, is by taking sections of them, taking what we need from them and implement them to the task at hand. For Internet of Things, I am not certain what the meaning of managing Internet of Things is. If you could give me an idea of what that means.
Well, imagine that you have a security problem in an environment.
Mm-hmm.
Yeah. What kind of functions, cognitive functions, do you need to solve that problem of security, human security?
Human security. Okay. Well, first of all, it's based on what I know, what little I know of the fact. But initially, attention. It's an obvious one to know when something is wrong with a person. Then the different elements of memory, it could be to know what each person is predisposed to, and followed with knowledge from what we know about people's health, for example, or the social situation of a given area, as well as something that allows us to make plans with that regard. It could be for cases.
So different.
Thank you. So different cognitive functions must be activated depending on the problem that you have. Okay, there are some cognitive architectures like CST that allow to configure, to create a specific set of cognitive function to solve a problem. Yeah. So I think this is, as you say, is your first step into cognitive architectures, but I think it is not too bad. Okay. It's my point of view, obviously. Thank you. We don't have any more time for questions. We're going to proceed with the schedule. Now, is it in the room Frank Kruger, who's going to be presenting paper number 104, which is named Human-Robot Attachment, a Working Framework Based on Human. Is Frank Kruger in the room?
Felix, I contacted him and he is not responding. He actually was sure that his talk is tomorrow. I do not know why.
Okay. Thank you, Dr. Alexei. So maybe we can proceed with the next talk. Rafael Salazar. Rafael Salazar is right here, so he's going to be presenting the paper to us. Cognitive Architecture Configuration Model for Performing Dynamic Pervasive Service Composition. Thank you. Go ahead, please.
Okay. Good afternoon, everybody. My name is Rafael Salazar, and I'm going to present the job titled Cognitive Architecture Configuration Model for Performing Dynamic Service Composition. Okay, this is the outline of the presentation. We will start with a brief introduction, on which I would like to talk a little bit about pervasive systems. Thanks to some advancements in technologies such as wireless network technologies or battery technologies, we are now able to embed devices on today's environments in order to provide computing capabilities. Those advancements also make such devices capable of cooperation and coordination among themselves, which is the basis for creating pervasive systems. But these advancements also come with a share of challenges, some of which are like device availability, since we don't have any guarantee that devices are going to be present during the entire lifespan of the pervasive system. They might go absent, they might move away. Also, problem like device selection, we have to create techniques to select the most fitting devices for a specific task. The communication among devices, since they are mostly connecting through wireless connections. They are not very reliable most of the time. Also, resiliency, since the system will be able to adapt to failure, since there might be devices going in and out of the system. There might be communication troubles. Also, in energy management, since most devices won't be connected to will be connected to a limited source of energy like batteries, among other kind of challenges. This led us to ask ourselves, can brain-inspired cognitive architectures be a solution to that kind of challenges? Currently, there is no general solutions to this kind of problems stated before. But we do know of a system that is somewhat good at managing resources, both external and internal, in the tasks they are controlling, and that system is the human brain. So, thanks to this, we believe that a BICA can be employed to deal with controlling the devices in a pervasive system and engaging in pervasive service composition on top of the system. So, before going to service composition, we have to define what is a service. In computing, we define a service to the abstraction of a capability offered by a device. For example, a smartphone camera can be abstracted as a service, as can, for example, geolocation or time services in a device. There's a subset of services called pervasive services that are those capable of executing at any time, on any place, and with minimal user intervention, since they are embedded in the environment. But also, this same environment limits those services. So the services must be aware of their surroundings at any time. Regardless of the type of service, there might be user requests that are just too complex to be solved by a singular service. In that case, it will be desirable to be able to combine the functionalities of different services into one single composite service. The process of combining many services, we combine the functionalities of many services into one single service, is known as service composition, which is the problem we are trying to tackle. The service composition field has been going for many years, so many approaches have been used for service composition, among them machine learning, game theory, self-organization, genetic algorithms, among others. However, few of those approaches consider key issues such as, for example, the ability to adapt to a change of goals mid-composition, the capability to gain experience from past compositions to use on future compositions, or the need to have the services from the start from start to finish of the entire composition process, which might affect energy efficiency. We found only one work on all our literature review which employs a BICA approach, but it has issues with potential memory bottlenecks, since there is no attentional filtering between the perception models, perception functions, and memory, so it could saturate. There's also the requirement that it requires static devices such as desktop computers or servers to perform compositions, which might be unfeasible on some pervasive systems, and also it limits the service selection during in the composition, since it has bias towards the users on the devices, which might limit solutions, as well as it has the same issues that non-BICA approaches, which we consider somewhat a waste. With this in mind, we propose to employ a BICA, the quiet local BICA, which is developed by a group at Simvestab. And some assumptions and hypotheses of this proposal is that the Guadalajara BICA models are based on neuroscientific evidence. It's also able to compute the context to create a picture of the system's current state. It has a composition solution stored in memory to employ as experience and it can also evaluate a plan's execution, evaluate by step by step, at every step of the plan. And as a hypothesis, we have that a composition retrieved from experience will be faster and more reliable than starting a composition from scratch. And then the BICA can provide a composition of adaptability and resiliency to change of goals and resources during the composition process. The composition process is basically as follows. Those are the biological BICA's models. And the first step is that the sensory models, both internal and external, receive the inputs from the environment. They transmit it to the perception model where they are interpreted. And once they are interpreted, they are transmitted to both the memory models for storage and the motivation models to compute the current goal of the system. With both computed, it proceeds to transmitting to the decision-making model in order to query the planning model for past plans to solve that goal. Then the decision-making model decides among them to choose one, and then the planning model starts executing the plan with the monitoring model executing every step of the plan. For every step, the planning model transmits to the alert model which models are needed for that specific step, and then the alert model either inhibits or stimulates the cognitive models according to the needs of every step. The set of needed models and the connections among them, we call them a cognitive configuration. For this, we choose a particular case study about predatory crime detection. What is a predatory crime? A predatory crime is a crime that is deliberate and that takes advantage and take the victim's property, the same way of how a predator will take advantage of a prey. There have been instances of deployment of drones which help to deter criminals from committing crimes, or help them or help police authorities to capture them. One of these has been actually here in Mexico, we used to do. From this, we deliver additional assumptions. The first being that the environment is embedded with devices controlled by the biological BICA. And the second, that there are devices near every possible crime scene, so there are no blind spots or unreachable places. From this, we have that the system works in three phases, where the first phase is monitoring. In this phase, the system, as the name says, monitors the environment in search of ongoing or potential crimes. For this, it uses devices such as cameras, whose input will enter to the external sensory and then be interpreted in perception with the help of inputs from motivation. The input will be stored in memories, and we will check for associations to see if it matches with past scenarios of crimes or suspicious behavior. This information is transferred to the decision-making model to see if it's necessary to change phase or maintain monitoring, which might alter the plans. In case we maintain the monitoring phase, then we require the orientation model to guide the the sensory devices and the motor model in case we need to do some movement, for example, moving cameras around. And this results in motor outputs. In case it detects a suspicious behavior, for us, suspicious behavior could be, for example, a person being fully closed by another person, then we go to the third phase. In the third phase, the system has to send a drone to the place of interest, since we assume that the sole presence of the drone will deter the criminal. Here, we have to visually locate the place of interest. Once we locate it, we also maintain, we will have to look in case the crime is committed before we can reach the place, and that will non-declarative memory helps. The information is sent to the decision-making module to decide if we maintain deterrence or change to the next phase. In case we are still in the deterrence phase, we have to orient the drone towards the goal, which will need the help of the orientation and motor modules to maintain a correct orientation towards the place. In case the employment of a firearm is detected, either in monitoring or deterrence phase, we switch to alarm phase, in which the goal is no longer trying to deter, but to alert nearby authorities about the crime. In this case, the system can visually locate any device that it can employ to draw attention towards the scene. With the help of cameras, we have to look for association to see what kind of device we can employ for that task. Then decision making, we have to decide which one to employ. Then we query for plans, and the plan is executed by the motor module by activating the device. This is mainly the three cases of functioning of the system. And during the development, we run with some issues that we have for discussion. The first one being superhuman capabilities. We know that we humans are limited, sensorily limited, but some of those boundaries are not present in robotic systems. For example, there can be infrared cameras present in the environment, and we know that we as humans cannot see infrared vision. So one question is, how can we modify a BICA to behave correctly under such situations, to perform correctly, having such inputs that we normally cannot act upon? The second one is context. Since in real life, many situations can be misrepresented of its context. For example, if we see two children playing with toy guns in the street, we may be able to deduce that they are playing warplanes. But can a BICA do the same? Can a BICA reach the same conclusion? We don't know. And it's something we have to work for employing this kind of systems in this situation. Also, context is very important for pervasive systems, since any change in the environment, it can be critical for its functioning. Also, model granularity, since we load, in this work, we load, stimulate, or inhibit modules whole, but not individual submodules. For example, we load the entire motor module, but we only employ, let's call it, voluntary movement. But we know there is reflex movement, routine movement, etc. And still, we load the modules whole. So there's room to improve regarding that. And last but not least, ethical reasoning, because we assume that there is just one situation happening at a time, at any moment, for the study case sake. But that's not the case most of the time in real life. So if we have many situations happening at the same time, and I can only attend one or a couple, how can the system decide which ones are more important to attend? If the system is a critical system where the safety or even the lives of its users are at stake, that's not a light decision, and this goes beyond just resource management and goes full into ethical reasoning. And we are not sure that's something that BICA is ready to understand. So, for now, as a conclusion, we see that humans learn how to perform complex factorial tasks during their lives, and this is the inspiration from us to propose this system, this approach that is using a BICA to carry pervasive service composition. And we believe that despite these limitations, Such approach is promising to tackle this kind of open problems in the field of service composition. That will end my participation. Thank you for your time, and all questions and comments are welcome.
Questions? Yes, please. Our guest of honor.
Okay. It's quite interesting work. I think it's really full of possibilities. I was wondering here, in a situation that you have, for example, different environments, each of them monitored by a camera. Okay, you can think of cognitive architecture, for example, for identifying people moving around. Okay, and for example, using the clothes of the person, you can give a tag of identity to each of them. So I can call, oh, this is person A, this is person B, this is person C. Okay, but when this person moves to a second environment and a second camera is making the recognition of who else is passing through, how can you make the conciliation that okay, person A in one of the environments is equivalent to person D in the other environment? Because you can have, for example, different color calibration for the cameras, and then there must be a problem in knowing that the same person that appeared in one of the environments is the same one on the second environment. So how can you think about making this conciliation such that you can actually track wherever this person is moving around from different environments?
We were considering the part of when transiting from one part of the scenario, let's call it, to another, but the part of will be help with, for example, the memory. In memory, we have stored different episodes, different scenarios, different parts of, let's call it, scenarios. When we show a person as part of it, and then maybe transitions or movements, and I think it can be expanded to show not only as part, let's say, of one field of vision, but multiple fields of vision. Use scenarios as a concept of the entire environment, and that will help us. In case, let's say, that person moves from the field of view of camera A to camera B, that scenario construction will help us to track the transition, the movements of the same person. But that will be, we were considering that in case of, let's say, normal camera report. If there is a variation, for example, in that, close to that color, for example, that would be a little bit tricky because it will require not only to track the movement, but to make a recognition, an association that despite the changes of color, for example, it is the same person. I'm not quite sure how to call that different, but I am sure that the scenario built in memory it's a big part of how we will track different points of view in a same scenario, because that's how we normally build it in our brains. Not necessarily because we can say multiple fields of view at the same time, but because we transit the different parts of the scenario in periods of time, and that helps building scenarios. And I think that's part of the solution for this kind of things.
Is there any other question in the audience or in the Zoom room? No? Well, we're gonna proceed with the next talk. Thank you. Is Carlos Alejandro Sanchez ready to present us? Thank you very much. Go ahead, Carlos. Thank you.
Okay, hello everyone. Today I'm going to talk to computational model of the artificial function and attention. My name is Alejandro Sanchez. This is the agenda. Well, first we need to know what is attention. Well, attention is a process of selectively, actively, and economically extracting information. That means that attention always is selecting the stimulus in the environment and selecting what is important for the objective in that moment. In an economically ways means that is using the less amount of energy. And well, in the research of attention, we have a lot of taxonomies. In this case, we use the taxonomy proposed by Michael Posner that differentiates at least three main attention systems, that is alerting, executing, orienting, and executive control. In that image, we can see the brain and some areas that is involved in the functions. Well, alerting basically maintains an internal state in preparation for events related to tasks. That indicates when to pay attention and modulates the level of vigilance. The orienting selectively targets one or few items from numerous stimuli and amplifies its object of interest. Finally, executive control that decides how to process the information we attend to, selects the process that are appropriate for a given task and controls their execution. In this work, we work with alerting. But what exactly is the problem? Well, without an energy modulation, a system will all times consume the same amount of energy for any given situation. That means that doesn't matter if the cognitive architecture do a complex task with a lot of stimulus in the environment, or easy tasks in a controlled environment, the system or the cognitive architecture uses the same amount of energy in almost all the cases. So that is the problem. Our objectives with this work is identify the processes and brain areas that have an impact on awareness, design a neuroscience-based schematic model of the attentional processes of awareness, develop an inspired computational model of the alerting function, and finally validate the performance of the model by comparing it with the response in humans. Well, in the state of the art, we view a lot of architectures like ACTR, Arcadia, but the only architecture that do a little bit the same, like alerting, is LiDA. LiDA have alarms. An alarm situation is when an agent selects and executes an action to respond to a dangerous situation before aware of the situation. So that means that if you have a situation, a dangerous situation, the LiDA do a free pass to do an action, but this system, this alarm, no modulates other cognitive functions to this alarm, just do an action. And in the conclusion, reviewing all of these architectures, the attention is mostly approached as a way of filtering relevant information in order to carry out a response or a learning. And that no environment dependent or time-sustained alert or activation state is used in these models. In biological evidence, we can see that the ascending reticular activating system controls alertness and arousal through the functioning of multiple neurotransmitters. In the image, we can see some areas that are involved in this process of control alertness, and these areas distribute non-specific sensory inputs to various areas of the brain, alerting and preparing the cerebral cortex to process specific stimuli at the attended environment. Well, the areas function on the ascending reticular activation system have two main functions, that is activation and inhibition. The activation is due by some neurotransmitter like orexin, dopamine, serotonin, etc. And the inhibition, the same as some neurotransmitters like GABAergic that are produced in the BOPO, and this neurotransmitter modulates this functional alertness or the level of vigilance in the system. For our cognitive model, we use these areas. In this slide, we can see the whole system and all the areas involved in this process. And we can see up to the neurotransmitters involved, like acetylcholine, dopamine, serotonin, orexin, and GABA. In this model, also we can see the connections, like activation, inhibition, and the cortex. But before that, explain this connection, we need to know how components or these areas function inside the model. Well, each area will be related with respect to the intensity of excitatory or inhibitory inputs and their weighted weights. That means, for example, in this image, that locus coeruleus sounds to the tuberomammillary nucleus activate signal. That signals have a weight and is received by the tuberomammillary nucleus. And the tuberomammillary nucleus sound an inhibition signal to the locus coeruleus. This is just an example. And the mathematical equation is the energy of the level of alertness of this area is equal to the symmetry of the energy of this area multiplied by your weight. And the question is why we do that? Why do this simplification? Well, the literature does not have enough data on each neurotransmitter like production, consumption, and their interaction with other areas to make a more complex model. And we'll follow with the model we have in this slide, the activation connections. There are two main branches, like this, the first, the ascending pathway to the thalamus that activates the thalamic relay neurons, and the second branch activates the neurons in the LHA area, the forebrain, and the entire cerebral cortex. In the image of brain, we can see the same, but in brain function. And in inhibition, we have two main areas that innervated system, that is the ventrolateral preoptical nucleus and the parafascial zone. These areas regulate the alertness and promote the sleep. And finally, we have the output to cortex. That signals is where other cognitive function can take the alertness signal and adapt the processing of stimuli. An example, I don't know if the motivation function needs to know what level of alertness is the system in that moment, can take the signal in this area in the prefrontal cortex and adapt your behavior like the object is in that moment. In our model, we have two inputs. The first is the circadian rhythm. There is a rhythm that modulates our vigilance. That rhythm is modulated in the humans by neurotransmitters, by the light of the environment, and some other things. So for this model, we use a simplification. We do a signal, a sinusoidal signal. The second input is the senses, like hearing, like smell, taste, etc. The senses are processed by thalamus. In our case of study, we do an integration with the auditory system to tell the model. First, we have an auditory stimulus that is processed by the auditory system. This auditory system processes the signal, are your properties, and send the signal to a model called signal processing that compares that signal with the signal that this system, with the signal that before we hear in our memory system. Our memory system have two types of memory, like it is average memory and lost memory. This signal processing compares that two signals and send a new signal to the other system. This is for do an habituation in the system and send, and the other system finally send the outputs to a level of degree of alertness. For validate our model, we do an experiment inside the Oddball paradigm that consists in two stimulus. This one is the standard stimulus that takes 80% of the time of the set, and the Oddball stimulus that takes 20% of the time of the set. For example, if we have a set of 10 seconds, we do 80% stimulus of standard and 20 the Oddball. And we did that because each of the Oddball sounds appears, the human brain have a signal that is called P300 that appears 300 to 500 minutes after, milliseconds after this is Oddball stimulus. In order to obtain the human data, we use an emotive depth of plus to measure the signal in the human brain. The motive we can see in the image. This is EEG, electroencephalograph, and measure brain waves in frontal areas like AF3, F7, F3, F5, etc. We can see the areas in the overall. Well, what is the results? Once obtained the human data, we do a 3 sets. We change two parameters of properties of sound. That is, we change the frequency, we change the amplitude, and we change the time. That is, in our stimulus, the standard and the Oddball, we change these properties. We do the same experiment for each subject and obtain this data. So in order to compare this, we use a thing that is called similarity matrix. And the first step is compare with the subject one, the frequency, the data about your frequency versus your frequency, their frequency versus their amplitude, frequency versus time, amplitude versus frequency, and so on. And in this case, yellow means that is the same signal or more really similar, and 0 is totally different. And after that, we convert that matrix into a vector. So we have a vector with the comparative data in the subject one. And we do the same for all subjects, the subject one, the vector of subject one, the vector of subject two, and the same for others. And finally, we obtain the similarity matrix. This matrix is really important because we can see the similarity between humans. Why? Well, we can see that it's a little bit similar in the major of cases. If the results are different, if the behavior of each human was different to others, we cannot do a model of that because if this behavior have not similarity between each one. So in the row for gene, we can see the noise. The noise is totally different to the human. And in the sixth subject, we think that is just noise or a problem with the model. Well, with the model, we do the same. We do the same experiment with the same change of frequency, amplitude, and time, and take the data about a configuration 1, configuration 2, and etc. This configuration changed the memory, or this configuration was with the memory average, and the other with the memory loss. And we change the level of the circadian rhythm. And do the same, the vectors. And finally, do the similarity metrics, but this time with human versus humans, model versus models. And in the red square, we can see the comparison between humans and models. We can see that the first, that is the memory loss, are more similar with the humans than the models with the average memory. Well, that is important because our model seems to work. In conclusion, we can say that the model percent can behave in a similar way like human alert. Also, we can see that the model has a better performance with lost memory than with average memory. For future work, we need to add the functionalities of the different neurotransmitters to obtain more specific functionalities with each component and with other cognitive functions, and perform other integration with other cognitive functions such as vision, motivation, memory, etc. That is all. Thank you.
Questions? People that study attention, usually they split the problem of attention into two modalities, that is bottom-up attention and top-down attention. And your model seems to be quite interesting for modeling bottom-up attention, this idea of alertness and alarms and things like that. I was wondering if you think that your model could also be used for top-down attention, and if not, what could you put on top of it such that it can cope with top-down attention?
Okay, well, we think that the model we can use with top-down and the bottom-up. Why? Because these models are connected with other cognitive function and with the other two attentional networks, like this orienting and like this executive control. So in order of that, this alerting system receives all the information, I don't know, bottom up, top down, and modulates the awareness in that way. That is inputs of the cognitive system or the other properties of awareness of attention, and do
the process, and finally takes other level of awareness.
Any other question from the audience or from the Zoom room? Well, I have a question. I don't know if you meant to say that the model is better or has more alertness with the memory loss than with the average memory. Memory loss, you meaning that he can recall, or do you have data that you made some damage to the memory modules? What are you saying with memory loss?
Okay. Well, the memory loss basically in the model, when receive a signal, sound signal in this case, we start to losing the information in time. So remember, yes, but just a little bit is forgetting almost all. On the average memory, well, do the average between all can remember in that way, and finally obtain a signal that memory.
And how do you explain that difference in the attention? Why in one case?
So what is better?
Why is better? Yeah.
Why is better? Really, I don't know why is better the memory loss. These results indicate that it's better, but I don't know why really. Because in humans sounds weird that losing memory do better performance with our attention. So I don't know why in that model is better.
Thank you. If there is no more questions, we proceed with the next talk. Thank you.
Thank you, Carlos. Is here Tania del Carmen?
Tania, please. Okay, Tania, when you're ready, you can share your screen and have the mic on.
Hi. My name is Tania, and today I talk about the proposal for a computational model of synthetic memory. This proposal is divided in different parts: introduction, problem statement, objective, proposal, implementation, case study, results, discussion, and conclusion. This proposal is a component for a bigger cognitive architecture called Guadalajara. This architecture is composed for different cognitive functions, such as perception, attention, decision making, associative learning, associative memory, motivation, motion, etc. Acquire divided the memory into types: short-term memory and long-term memory. The long-term memory is divided in declarative memory and declarative learning, and implicit memory and implicit learning. The implicit learning is divided in 4 types: procedural, priming, associative, and associative. In associative, we found our proposal. To differentiate associative learning and associative memory, we consider that the associative learning is the moment which the system receives new information, acquired new information, and the moment with the model retrieve previously acquired knowledge. And the memory is when the system retains and stores this information previously acquired. In specific, the association memory, unlike other types of memory, is when you store the relation between 2 stimuli or between an stimuli and an incentive. Also, the associative memory is capable to retrieve knowledge through partial information. This characteristic is very important because with this characterization of system can generalize human responses. The problem statement is that through the review of the literature, we found that some works consider associative memory, however, they don't model it. In addition, cognitive architecture do not consider an associative learning and associative memory model that can function independently and distinguish between a learning process and a memory process, as humans do. For this reason, our objective is create an associative memory model based on biological evidence that is capable of functioning independently other cognitive functions, and that can interact with them to create a cognitive architecture that describes more human functionality. Our proposal consists in 2 stimuli: an incentive value and visual stimuli. This stimulus is for generate memory. Later, we use a visual stimuli for retrieve this information previously stored, or visual or incentive value. Our proposal begins with a conceptual diagram or a general process. This general process is made because is realized through review of literature. In this review of literature, we found brain structures related to associative memory. These structures contain different processes. This process we use to extend general model and create to process model. These processes are divided into phases. The first phase is a generation memory, and the second phase is a memory retrieval. With these models, we implemented on the middleware for a cognitive architecture. Its implementation in this middleware will allow us to have a distributed model. The big nodes represent the brain structures found previously in a general model, and while the big modes represents the process found for each brain structures in general model. Later, we validate our proposal in a case study. The case study is divided into experiments. The first experiment consists in memorize 5 visual stimuli and their respective incentive values. Afterward, the associations retrieval is carried out in 2 ways. First, retrieval of the incentive value from the visual stimuli, and retrieval of the visual stimuli from the incentive value. Finally, we use a partial information with noise with Gaussian noise. For the 2 experiments, we use only partial information or similar stimuli. This experiment is important because with this experiment we verify that the proposed model can generalize. The first experiment, 2,000 iterations were made for this experiment. In average, 25 iterations is necessary for the phase for memory generation phase, and 50 for the fish, 56 for the salad, 61 for the pizza, and 92 for the cooking. For the phase 2 retrieval, we use visual stimuli for the first part. All the rest we use incentive value. We obtain the results with a correct stimulus previously associated, and the error is acceptable because it is very small. And the second part of the experiment 1, we remove 50% of the original image and added Gaussian noise. In this case, we obtain 1,013 iterations for obtain the correct associated previously used. In the experiment 2, we use partial information, and we can see that the stimuli associated is correct. And finally, for the case of generation, we use different visual stimuli, similar stimuli. In this case, we can in this case we obtain that our model is capable to generalize because we obtain the incentive value similar to the original stimulus training. Finally, we obtain that the creature endowed with the proposed model can retrieve the information from inputs without noise, with missing information and its associated stimuli as shown in the case studies. The model was designed to work independently or a part of a cognitive architecture. When generalized the memory and analyzing each stimulus, we notice that the incentive value converges faster than the visual stimuli after observing that the hero for the incentive value falls with less slope than the hero for the visual stimulus. The higher the incentive value, the faster the memory generation as shown in the literature. We observe that the model is capable to work in bidirectionality, which is an essential characteristic because the human brain is capable of remembering food from a motivation with other cognitive functions. The retrieval experiment showed that if a stimulus is not displayed clearly, noisy, or incomplete, it is more difficult for the system to retrieve than for a person. In addition, we show our model was capable to have the characteristic of regeneration by making the creature capable to retrieve the associated value through input stimuli that partially diverge from learning stimulus. Thus, generalizing the response obtained, we consider this result very important, mainly because the generalization is essential for the adaptation of the creature size, it allowing to respond to similar situations. And finally, the implementation in middleware has different advantages. Perhaps most importantly, it should be easy to test and improve the results considering the integration of our model with other cognitive functions. That's all. Thank you.
Thank you. Is there any questions in the room? Yep.
Hi.
Why am I asking?
I was wondering that in your experiment you have used 5 different stimuli. Okay, what you think will happen if you scale that and have a large number of stimuli? Let's instead of 5, you have 1,000. Do you think that it will work more or less the same, or you think that some different kind of things could happen?
Our model have limits. In this case, we see that the 11 of 5, the visual stimulus, when it is retrieved, we see that 2 image appear overlap. In this case, is a error. And in other cases, for the incentive value is approximate, a difference for the visual stimulus have minus errors, but is failed already to 20 or 25.
What happens if you connect your function with attention?
When we connect we obtain more faster the memory. In the phase of memories, in the phase of generated memory, it's more faster. It's incremented when we connect.
Okay, and you think that is because you extend the number of objects, or you reduce the number of objects? What is the effect of the attention in your proposal?
When we omitted the learning we are more response is the
Any other question from the Zoom room? Well, now we're going to give the word to Dr. Felix for the closing remarks. Get ready your wine, your cups.
Okay, with this presentation, we get the end of this BICA conference. So, dear BICA members, authors, presenter, it has been an honor and pleasure to share with you and host this recognized international conference of BICA 13th edition. The BICA Society in Guadalajara continue to work for this organization that is now truly international. Exciting and vigorous. We ought to remember that this year we have new members of the board of this society. Thanks to the hybrid format adopted this year, we unfortunately miss the opportunity to meet each other in person. However, we also have some advantage. We have more than 160 submissions, and we have more than 60 talk presented. We had 5 lectures given by keynote speakers. We had 62 posters were online displayed. From the rush of the first session to the light on a small earthquake here in this facility, the third day we have sincerely enjoyed every minute of this meeting due to the delightful exchange of sincerely acknowledge that you participate with us, we share with us, and we thought that your experience that you share obviously will benefit not just the community, but obviously for all the readers that our works attain. That is great to try to contribute to the knowledge of this environment, this society, this community, and the whole world. Well, for us also, in the name rather of the core of this organizing committee by Felix Ramos and Alexei Sansonovich, David Kelly, as well as Dr. Jonathan Rosales, Dr. Francisco Robles, and Dr. Antonio Cervantes. We are very happy and we were very honored to organize this 13th edition of BICA AI. Well, I have no more to say that it's a pity that all foreigners are not here because now the last event of this BICA 13th edition is to have a cup of Mexican wine and a small discussion of everything in the life, but mainly what happened in this conference, what we think about this conference, and what we hope of the next edition of this conference in China. So was great to have you, even virtually. And as I say, it's a pity, but we are going to say school, salud, taste, trust, cheers, and everything with you, even virtually. Be happy, and I hope to see you the next year in China. Alexei, I don't know if you want to say something, or we say the end of this conference at almost 15:39 minutes in Mexico.
No, I just want to say that I'm happy that BICA is still growing, and now we can celebrate its next success during recent years, the biggest number over several years in attendees, in talks, submissions, and so on. And I was really impressed by the quality of some presentations, by the organization of this event, by the number of tracks and talks and panels. So yes, I'm happy about this conference, and I'm looking forward to the future. Thank you very much, Felix. Let's congratulate the President Chair for his big work and big achievement. Congratulations, Professor Felix.
Thank you. Todos acérquense por acá, todos. Pero vamos a tomar una foto. ¿Cómo se pone esta sola? ¿Cómo se pone ahí grande? O que nos vean nada más a nosotros.
Mejor que lo agarre, copa. Porque creo que ya esta se va a quedar bloqueada. Por el movimiento, está diseñada para el movimiento de estar enfocando.
Ok. Sí, vamos para allá. Vamos todos para allá.
Ya se vio el chupe. Déjame acomodarla para que no se vaya a cuadrar. A ver.
No nos vemos.
Ahí están los hijos, que los hijos aprovechen a los hijos. A ver.
O que los hijos se aprovechen de los padres.
Pues hay más o menos, muchachos, para que todos conozcan. Para esa que está ahí en medio, ahí nos están grabando en este momento. Entonces es grabación, ya se pueden acomodar todos para la
pero pasa una ropa de niña.
Eso nomás es para mí.
¿Qué pasa? Una cosa.
Pues sí, yo no sé por qué se come. A ver, ¿qué más? Una vez.
No, como no se ve, Jonathan,
Thank you for conference. Goodbye.
Cheers. Shall we drink now, or would there be a toast? I have my glass.
Cheers! Cheers!
Cheers! Oh, no. Cheers.
Salud!
Cheers. Great. That's water, by the way. Or vodka. Up and come. Okay.
Piłka.
Cheers.
Cheers, Alexei. Cheers.
Nazdarovia.
Nazdarovia, dice el doctor Félix.
Nazdarovia, Alexei.
Thank you. Thank you, Felix.
See you next year. See you next
Hi,
year
Hor.
in China. I hope to see you in China.
See you in
next year.
China, yes.
Yeah. Have a good year. Thank you. Wonderful conference. Wonderful.
Yeah. Thanks,
Alexei,
everybody.
I'd like to add that I agree with Rosario Cervello that said yesterday that one of the main BICA challenges now is to preserve and maintain our community.
Yes.
To keep our
That's
personal
right.
contact and our friendly and inspiring BICA here. Do this.
And I'm sure we will keep it.
Cheers.
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 Bye.
Bye. Bye. Bye, everybody.
Bye. ¿Alguien quiere agua? No, ¿verdad? Te oxida.
Ya dejen de grabar.
Ya, para ya.
Recording stopped.